Okay. So I don't
Just making
forget.
sure you guys can hear me, right?
Yes.
All right, awesome.
I mean, your image is a grayish black blob, but you know, we can't.
Yeah, nah, I'm using my desktop. It doesn't have a camera, but if I need one, I can go get my laptop.
Okay. Nope, we can hear you just fine. Yeah, let's see. We still got about 2 minutes. I'm just cleaning up a few things here. And I'm going to leave my email open because I know people are going to be sending me emails. I can't get this to work. Like I said, I'm not good at being the IT guy when I've got 50 people here. So I don't do a very good job of it. So, there's the phone. Okay. Somebody's asking me. This is Scott. Here's my meeting info. Technician license class. Go meeting invite. And oh, great. It doesn't show it. Wonderful. I don't. Okay, so you may be able to dial in. Let's see. Okay, so God. Well, I would say let it do it. Are you using the Zoom app? Are you using the Zoom app or are you? Yeah, you want to use the Zoom app if you can. Okay. And you know, the other thing is if you have an iPad or a phone, you could always use that too. Yeah, either way. So, you know, at least then you'll get audio. Okay. All right. It's 8 o'clock. Let's start, shall we? Okay. Well, I don't know how many people are going to show up. That's okay. You know, I had 65, 70 people on the list. I count 27 right now, including myself. So I'm okay with that. You know, people will probably be dropping in and out. It's it's a Monday morning and how sick am I? It's a Monday morning. I have a full-time job and I took the week off. And what do I do with my week? In addition to doing stuff around the house, what do I do with my week off? I teach a radio class. So
share yourself with
yeah,
those of us aspiring to be like you. Thank you, sir.
It's a bad habit. It really is. But you know, I find it worthwhile. So anyway, if everybody can see me, hi. And hi, Kathy. I recognize you from the other day. It's too bad we couldn't. Too bad we couldn't twist your arm to get on the air, but that's okay.
Oh, we will.
You can't blame me for trying. So
yeah, thank you.
I hope you had fun. So okay, so let me ask: did anybody here make it out to field day this weekend?
Yeah. We did. Yeah.
Excellent. Anybody else?
I did.
Sarah, where'd you end up?
I was at Jasper State
You were at
Park.
Jasper too. Okay. Now I must have missed you because it was a pretty big crowd and I didn't see you there.
I was in the afternoon, probably from about 2 to 6 or so.
I was gone from 1 to 6. And then I
Sure.
came back at 6 o'clock. So we missed you there.
Yeah.
Did somebody get you on the air, I hope?
Actually, no, I tried to get on HF, but it was really busy and really just bad propagation. But I had fun listening to Matt and Nathan and Jeremy, and I'm walking by and Joyce said, "Oh, I recognize that voice." So I got to chat with her and Laura. It was pretty fun.
So let me point out that that's not all that uncommon. I've run into many people who I did not know what they looked like, but I knew what their voices were because I've talked to them many, many times. That's a very common thing. So, all right. Yeah, I heard that there was some issue with one of the HF radios. The power was turned down a bit more than it should have been, and it wasn't working as a result. So, but cool. Anybody else make it out to field day this year?
I did.
You did. Let's hear it.
Yeah, we had a real good crowd in Anderson. We had it on Lake Hartwell. It was really, really awesome. I mean, it started early that morning, continued on until the weekend. It was awesome. Got to meet many, many different people.
And how did you guys do a sleepover or?
No, it was just a 2-day event,
Okay.
Saturday and Sunday, but it was awesome. I was there both days.
Cool. Anybody else make it out? Okay. Well, not everybody can do it, but that was one of the things that I'd sent out a note about. So here's part of our photos from field day this year. And yes, the grass is already brown in Oregon. Hey, is that Max right there? Right there?
There's Kathy. Yeah.
Yeah, and there's Max.
Yeah, there I am. Yeah.
There's Max untangling some wire.
Some ground wire. Yeah, it was a ground lead. Yeah.
So yeah, we ended up operating overnight. We ended up with over 700 contacts made all over in 46 states, just using a bunch of wires. So we're going to get to how in the world that can possibly work. That's actually one of my favorite things to talk about is antennas. So, well, let's see. So we'll quickly go around and introduce ourselves. I'm Scott. My call is N7JI, as you can see. If you have a call sign, feel free to change your name to having your call sign on it, so I know. If you don't have a call sign, hopefully that's the point of being in this class. We're gonna learn all the background stuff that is the fundamental underpinnings of the thing that is ham radio. So if you think this is just basically, I'm going to read you questions and answers, and you're just going to remember that, that's not what we're doing. So I consider that to be a better way of learning, the fact that we're actually going to learn the theory behind it all. As such, if we're going through the theory, my goal is to make sure that you guys actually understand the stuff that makes all this stuff work. So if we get to a point that you just don't understand something and you want to cover it again, you're probably not the only one, and feel free to ask and say, look, I don't understand that. Can we go through it again? So I was also in this particular case, because I looked at my schedule and said, I think I can do this. The question pool for the general is ending, that's rolling over at the end of this week. Let's have a party. We're going to say, we're going to teach it one last time. And the goal is that the technician and general exams are actually similar enough that somebody who goes through and understands, if we've had this class in the past, what I've noticed is that people who go through and understand the basic underpinnings of everything, how to make an antenna a certain length for a certain frequency, how to how to apply Ohm's law and stuff like that, what decibels are, you know, the things that are the fundamentals, the engineering fundamentals that say why ham radio works, propagation and things like that. I cover that anyway. And the technician exam, if you have a little bit more information under your belt, you'll find that the general exam is almost the same. You know, the theory behind it is exactly the same. It's a little more complicated the further you go, but I tend to cover it anyway with the interest of making sure that people actually understand it. So what we really end up doing is when we get, and somebody's got some feedback there. There we go. I think I killed it. And it's Yanni's phone. Okay. So what we end up doing is if you get to the point where you're comfortable with the technician stuff, you've studied for it, because I can't study for you. I can only give you the, you know, the encouragement and the I hope everybody's got, you know, been studying the material and done some practice exams, because you can't go into a practice exam cold and expect to pass. But once you're comfortable with the technician exam, the general exam is basically just different privileges, different power levels, different modes of operation, but the basic stuff underneath it is exactly the same. You know, safety is safety, and Ohm's law is Ohm's law, and you know, the speed of light is equal to the frequency times the wavelength. Once you know all that, it's always the same. You know, the information is the information, and it just applies a little bit further. So my goal was to, you know, make available for you an exam on Friday if you want to take it remotely. That's going to be your last chance to do the old question pool on the general before it rolls over. That's June 30th. So
Rod, is there any chance that the club would put on a test on Friday so we could have a local exam?
that's a good question. That's a Riley question.
Yeah, okay. I'll contact Riley and see.
I would contact Riley.
Yeah,
And
thanks.
my guess is that if he's available, he would be happy to do it.
Yeah, because our internet connection isn't the greatest, and I don't know that we can get all the videos set up for the remote test.
Yeah, so just ask Riley.
Okay.
Let's see, other stuff. Let's see. I've had my license since I was 15 years old back in 1984. I'm now 54. Ham radio has given me a path to get through engineering school, as well as picking electrical engineering as a degree, major, master's degree, getting jobs, getting a deeper understanding of, you know, how things work and how to use your hands, and how wires interact with each other. And it has given me friends all over the world. I've literally operated from, I don't know, 8-10 different countries around the world. And I have friends all over the place that I've made, and not to mention the fact that I really enjoy getting on the air and operating and seeing what I can do with as little as possible. So I'm, in that regard, I'm a very happy minimalist. For instance, probably the most impressive, and you'll understand why this is significant. The most impressive to me contact I ever made was from Oregon to the South Cook Islands in the way out in the South Pacific, using single sideband at 500 milliwatts, and got a signal report of 5.9, like armchair copy, as they say. So I like doing as much as possible with as little as possible, just to see if it can be done. So what we're going to do is we're going to spend just a little bit of time going around the room, and people are going to get a chance to introduce themselves, and try to limit yourselves to, I don't know, 30 seconds or so. So think about what you want to say, and we're going to start. And once you're done, you get to pick somebody, because everyone can see everyone's names, and you get to pick the next person to go. So I'm going to go with David Heath.
Oh, hi, good morning. Yeah, my name's David Heath. I'm here with affiliated with a club, Willamette View in Portland, Oregon. We have about 10 members and we got an antenna on top of a 7-story building, and I'm trying to get my license and so I can become active.
Awesome. So what's your background and how did you find out about ham radio?
Well, I've been exposed to it by my uncle and friends and that for a long time. I'm used to be involved in the electronics business, so I have electronic background. So those fundamentals I know pretty well. I don't know all the acronyms and jargon that goes with it that you just have to memorize. So
Okay.
but I've been doing pretty good on the practice test, but not just on the border. So I need to brush up on a few things.
Give you a little push.
Right.
All right, David, pick somebody.
Oh, I don't know. We could pick. I don't know who this Moto G is.
Moto G, Matt. Take it, Yanni.
That is Yanni. Yes, that's me. But I lost the picture, and I'm there. We are. I think yes. I'm Yanni. I'm from Virginia Beach. Live in Virginia Beach, actually. I'm from Canada originally, and I learned about ham radio in a few years back. But I finally got my basic Canadian license, and now I got the U.S. technician license, and I'm going for the general for better understanding, I guess, and more practice through the travels around the world with the boat. Next person, I guess. I can't see in my phone.
I'll pick one.
You pick one.
William Durando.
Yes, sir. My name is Bill Durando. I am a police chief of a private police department in Northeast Pennsylvania. I apologize. I'm driving. We actually had an emergency this morning. I'm on my way to work. Been using radios for years with work. Always been interested in ham. Just never made the jump to schedule a test to take a class like this. Well, a month or so ago, a CERT team formed in our community, and I am the go-to. Like, they report to me, and a lot of them are hams and wanted to know if, we'll be using that. And I said, well, I better get on the ball and get that done. So that's, it kind of gave me motivation. I've always wanted to do it, always playing with radio since I was a kid. My dad was a cop, uncles, all kinds of stuff. So I've always been around radios, just never amateur radio so much. So kind of lit a spark for me to get it done. And I apologize, I can't, I'm driving.
Nope.
So I can't
Nope,
see
I'm
the
picking the next one. How
Thank you, sir.
about Doug Morrison?
Hi, I'm Doug Morrison. I live in Reedsport, Oregon. I work for the Confederated Tribes of Coos, Lower Umpqua, and Siuslaw Indians, and that's part of the reason why I'm doing this. Is we're trying to put up an emergency communications web through all of our tribal outreach offices. I got involved in radio stuff back when I was a kid on CVs, and I figured we'll take it to the next level.
Do you know Melvina? Do you know Melvina Adolph?
That name sounds really familiar.
Yeah, she's the mom of Scott, who I know here. She and her husband live in Reedsport, and they both have their licenses. So you may want to look them up.
Oh, okay. That name sounded real familiar.
Yeah. All right, pick someone, Doug.
Let's go with Pat. I'm gonna probably destroy your last name, Mussman.
Mussman, yes. I'm Pat Mussman. I've been into radios like William. I have been working in security, and I have loved ham radio since I was in my 20s. Always wanted to get my license, and I'm 65 now, so I'm going for it.
And where do you live?
I live in Grand Island, Florida.
Okay. And that's actually a pretty common story I hear. Wanted to, didn't have the time.
I have a house full of radios, just can't get on them.
Yeah. All right, Pat, pick someone.
Mary Ellen.
Yes, I'm W4YMU. I got into ham radio Oh, when I was a teenager, because I was a CBer, my great uncle used to own 3-story Magnum box, so I've been surrounded by radio forever. I'm also into weather. I'm also a storm chaser, and then if I pass my other exam, I'll be your meteorologist researcher. So I will be touring the coast coming up really, really soon. What I'm trying to do is just upgrade to general, taking baby steps on this, and eventually I will go for the extra class and maybe be EC.
Cool. All right, Mary Ellen, pick someone.
Allison.
Let's see, Allison.
Just trying to unmute myself.
There we
Sorry
go.
about that.
Hey.
There we go. So interested in ham due to rally racing and needing to get my ham license so I can be a radio operator with my other volunteer duties there. Currently live in Minnesota, but in sunny Florida, visiting family.
Cool. Somebody's echoing. Don't know who, but go ahead, Allison, pick someone.
All right, Steve, what's your story?
So I'm Steve, KK7ETF. I live in Utah right now, but my wife and I are planning to move to Georgia soon. So we'll return to my background in the South, in Tennessee and Louisiana. I've had my technician license for a little over a year. I didn't have a lot of technical background. I'm a retired professor of Latin and Greek. So I've got plenty to do with my time these days, that's for sure. My story about the radio, I had a great uncle when I was a teenager who lived in West Point, Mississippi, and he was a radio operator, very known among that community down there. And he kind of inspired me. I got my license when I was, I think, 16, but then I went away to college shortly after and let the hobby fall. But I've gotten interested in it again, and I'm very focused on Morse code. As the language professor, the language aspect of Morse code has really been fascinating. So I'm going for the general, and I guess that's about my story.
Cool. All right, pick someone.
How about Yanni?
We already did Yanni. He looks different now.
Yeah, I'm on my laptop.
All right, I'll go. How about Jen?
Hi, Jennifer Meyer from Elk Valley Rancheria in Northern California. Been trying to get my ham license. I've just been really swamped with work, so I'm trying the class again. He's a great instructor, just saying.
And where do you live?
Elk Valley. It's Crescent City, California.
Crescent City. So is that Del Norte County?
Yes, it is.
Oh, cool. Okay. Underrepresented during the California QSO party, by the way. Very much underrepresented. Pick somebody, Jen.
Let's see. I got in a little late. Has Chance gone yet?
Chance has not.
Hey everybody, I'm Chance. Pretty young. I'm 26. Been into ham radio for a couple of years now. Figured I should actually get my license. I've just been listening into everyone around me.
Yeah, you're gonna go to the fun side of it.
Yeah. I've always my main goal with it is to be able to contact the International Space Station, because that just seems lit.
And where are you located?
Connecticut.
Connecticut. Okay. Oh, you're right near ARRR headquarters too.
Oh, really?
Yep.
I didn't know that.
They're in Newington.
Oh, actually, I think I work literally like 3 buildings down from them. Actually.
Do you really?
Yeah, because I noticed there's a big AARL building, and I was like, I'm pretty sure I'm gonna have to go get my test there. I didn't know that was the main one though.
Mm-hmm.
That's good to know.
That's 225 Main Street, Newington, Connecticut 06111.
You know more about Connecticut than I do.
Uh-huh.
I've been living here for 26 years.
All right, pick someone, Chance.
Bobby May, have you gone?
I'm doing good.
I'm originally from Mayfield, Kentucky. I live in Merlin, Oregon, and I just got my technician license last year. I promised my uncle I would get my license, and I got it about 2 weeks after he died. So now I'm going to go for my general.
Awesome. And Merlin's down by Medford, right?
Yes.
Between Grants Pass and Medford?
Yep. Well, actually, we're past Grants Pass.
Right, between Grants Pass and Medford. Okay.
No.
Oh, you're north of Grants Pass. Okay.
Yeah, north of Grants Pass.
Okay.
Out in the boondocks. When you start hearing the banjo music, you know you're getting close.
Okay, pick somebody. Or I can.
How about Johnny?
Yeah. I am Johnny K7ZZQ. God, can you see me?
Yep.
Okay, just Johnny K7ZZQ. And I know you look familiar, Scott. I took a CW class from you a couple years ago in the October and the fall time frame. And I need to do that again, obviously. But anyway, I live here in Mesquite. I'm an extra. I've been a ham since '94. And we put together a ham radio suite in our STEAM center. Well, most of you know it as STEM, but we have arts as well in our STEAM center here in Mesquite. And we're going to be teaching some classes, beginner classes, and I would just like to see how you do it or others, you know, so that we can be more effective in our training when we begin this coming August.
Awesome. And what ages is it geared toward?
You know, it's going to be open to everyone in the community, plus all the kids in school. So we have a wide range that we can select from.
And if it's Mesquite, is that Nevada?
Yes.
Okay. Very cool. All right, pick someone, Johnny.
You know, Phil, you know who I'm going to pick. He's the president of our club.
Let me unmute here. There we go.
Whoa, we got some echo. Turn down your volume there, I think.
I'm going to turn it down just a little bit. Let me get it over here. That.
Whoa.
Nope. There we go. There we go. We got to turn down now. There's still a little bit of an echo. Anyway, my name's Phil Capizzi. I'm affiliated with the Virgin Valley Amateur Radio Club here in Mesquite, Nevada. Like Johnny said, I'm the acting president right now. And we also held our field day this last weekend, which we had a small turnout as far as operators, but we had a good running in contacts. Been in ham since about early 2000. Got involved thanks to a neighbor of mine. Things up there kind of died out after he passed away. And then we went to, I came here to Mesquite and got involved with it and love it. My call sign is KE7WXY.
WXY. That is a mouthful on CW, isn't it?
Yeah.
Well, but it's a good call sign sequentially, easy to remember.
Yes, it is. I'm taking this so I can hopefully come Friday, I'll, with some extra studying in the evenings, go for my general.
Cool. All right, pick somebody.
Has Vic been picked?
Yes.
Okay.
No.
Oh, no, Vic Dietz has not been picked. That's right.
All right, thank you, Phil. Good morning, everybody. My name is Vic Dietz, originally an Iowa boy, now living in Chicagoland. Wanted to do radios all my life. I grew up watching my dad talk on the radio while he was flying the airplane and things like that. Got my technician a few years ago, and it's time to upgrade to general. So that's my goal. And we'll try and get it done this week before they change the question pool again. I have been able to use my license a little bit. Probably the most satisfying one was to go out and help with a 5K road race on Thanksgiving Day last year. And I stood one of the volunteer positions with my little handy talkie and watched everybody run by dressed up as turkeys. And it was a good time. It felt good to be of service to the community. So,
well, and you're in Chicagoland, right?
I am
So,
suburban Chicago.
so speaking of public service events, we provide public service because we have mountains here. You don't have
Right.
them in Chicago.
No.
We have some pretty big mountains and a lot of woods that tend to catch fire sometimes. But when they're not on fire, people tend to, crazy people tend to take their mountain bikes and go for long rides in the mountains. Or ultra marathoners tend to like running up and down those mountains. So we provide communication support for a 200-mile mountain road race, foot race.
A foot race of 200 miles.
200 miles. It's an ultra marathon through the Cascades. So we provide communications for that. So if you ever feel like coming out here and doing some really heavy duty support where there's like literally no communications, it's a lot of fun.
Sounds like a good time to sit and watch other people do that.
Doesn't
Sounds
it?
good to me.
You want to pick somebody else?
How about Sarah Hunter? Can you talk to us, Sarah?
No, I haven't.
Please go ahead.
Let me start my video here. Hi, everybody. I'm Sarah Hunter from KJ7LCX, Sarah from Blue River. My partner's been licensed for about 10 years and kind of was hassling me. And so in 2019, I took Scott's class, pre-COVID, got my tech license. And then because I live in a small community in a river valley outside of Eugene, radio is a little bit difficult. So I'm heavily reliant on the repeaters. Learned how much I didn't know and should know at the Holiday Farm Fire. And so now I'm like learning lots more about radio and how much we need radio communications. The most that I use my radio is I'm apparently known in the digital world around here for using my APRS radio and beaconing my location every 90 seconds when I'm trail running by myself so that folks can find me when something happens. And I can also text from that radio, which I think is really cool because then I get to run by myself and I stay sane and lots of people can find me. And sometimes I've had radio friends call me and say, hey, your radio hasn't moved. Are you okay? And it's like, yeah, I forgot to turn it off.
Can everybody see where she is? Like way out. I mean, this is, along the river.
I'm further south or further down river, Scott.
Okay. There's Rainbow. And notice this Holiday Farm RV resort. Everybody see that? That is where the massive fires started a couple years ago that made it almost all the way to Eugene or Springfield, all the way to here. So this whole area was basically on fire for like a month. And people learned a lot about emergency communications during that time.
We learned a lot.
Yeah.
So let's see, how about, has Steve KK7ETF gone yet?
I have gone yet. I've gone already, Sarah.
Oh, okay.
How about
sorry,
Pam Zumwalt? How about Pam Zumwalt?
Okay.
Pam? It says Zumwalt, but okay. Okay. How about Jared?
Jared's here.
Go for it, Jared.
So I'm living in Cave Junction, Oregon, slightly outside of it, out in the sticks.
Go
Very
caveman.
familiar with where Merlin is.
Go
Yes.
go caveman.
Yep. So I'm prior military, and I got to use some radios while I was in the military. I liked them. I liked how far they could reach. And after the military, I searched high and low for good radios that could do anything close to that, and came up empty, buying all the blister packs at Walmart and Best Buy that I could buy, and being thoroughly confounded at why they could list 47 miles, and I was lucky to get a mile and a half. And so I had always looked at ham radio with a little bit of apprehension because it has to have a license, and that's a strong gatekeeper. And then as I was in Tucson, Arizona at Davis Mountain Air Force Base, and then as I came back home to Oregon, I realized as I'm going through emergency preparedness that ham radio is actually not that scary, and it does everything I'm trying to do. And so I am the local emergency preparedness coordinator for my church out here, LDS, for those who know. And so I'm trying to get on. I've been studying off and on. I downloaded an audiobook to do the technician and the general, and I've listened to all of the technician and part of the general, and then your class came along, and I'm like, oh, let's just do this. And I'm currently in the process of signing up for the test to just be like, let's do it finally.
Cool.
So
Okay.
that's me.
Okay. You want to pick?
Has Jen Meyer gone?
Yes.
How about Johnny?
Johnny went.
1.
Yeah, I'll pick. How about Mara?
Yeah.
How about Mara?
I'm Mara, and I'm from Oregon, and I got interested in radios when my dad, I think when he retested, I think he has a general, I'm not actually sure, but yeah, I just think it'd be really cool to help him out.
So what do you do? What's your story?
Not really anything, just school.
Oh, okay. Where and what?
I go to school in Silverton, and yeah, I don't really know what else to say.
What year?
Going into 9th.
Going into 9th. Okay, so that means high school.
Mm-hmm.
So that means you're potentially the incoming president of a yet to be defined ham radio club at high school.
Probably.
Yeah. So there you go. Cool. All right. Pick somebody, Mara.
How about Johnny Bartley?
John Bartley.
I do believe I've unmuted now.
You have.
I have a technician license, which I acquired volunteering for Red Cross Disaster Services, and want to upgrade. I live in the southern suburbs of Portland, and growing up in South Florida, disaster preparedness was a must. Peaceful, placid Oregon, well, they keep talking about the big one coming sometime, and that's why I want to upgrade, because the airwaves are going to be flooded locally, and I'm going to need to reach out and talk to someone means having a general.
Yep.
How about Zumwalt? Have we heard from Zumwalt?
Pam, you have your audio?
Hi.
There we go.
I'm in Eugene, Oregon, and I have my tech license, but I'm not set up yet. We recently moved from the McKinsey fire area, and we're going to be building soon. And
do you know Sarah?
I've talked with her before briefly. Yes.
Okay.
I know of Sarah. And my dad was a CBer. We had radio in our house all my life, so I guess that's what sparked my interest.
Okay. You want to pick, or shall I?
Oh, sure. Has Has Anthony gone yet?
Don't think so.
AC3UCB.
Anthony?
Good morning, everyone. Anthony, KC3 UCB technician class from the Eastern Shore. Looking to get a refresher on technician class material and study for my general.
So what part of the Eastern Shore? Are you down toward the water? Or are you more up
Maryland.
toward, yeah, more toward Delaware or what?
No, closer towards DC.
Okay. So like Kent,
We're in the DC suburbs area.
like Kent County?
Charles.
Charles, okay. So you're okay. Cool. You want to pick or shall I?
If you don't mind.
Okay. How about we're getting close to the end here. Has Jared spoken yet?
Yes, sir. I'm Cave Junction.
Oh, you're in Cave Junction. Okay. See, I'm starting to. Okay. How about, okay. If you haven't spoken, just unmute yourself and start.
That's cheating.
Good morning.
Okay. So we've got we've got Eric and John. Eric, go first.
Good morning. My name is Eric Van Zant, and this is my boy buddy. It just popped up. I've been a tech for a while. I got involved with search and rescue and looking to get my general right now. And I live in Canby, Oregon, just south of Oregon City.
Cool. Okay, John, you're up. KC7 Bravo Whiskey Kilo.
That's Big White Knuckles. Hey, my name is John. I live in Florence, Oregon, and McKenzie River is not all that far up there. I used to work up there. And I've been here probably pushing 45 years. I've been a ham since 1995. And I'm looking to go towards my general.
Do you know Ralph?
Ralph?
Ralph
Yes.
Ralph Garono?
Toronto, yes.
Yeah, okay. And Jay Getler. I saw Jay this weekend at
Yep,
our
I know Jay as well.
Cool. Okay. So you're familiar.
Yep.
So
I've been
you're-
a member of the club over here for probably 26 years.
Cool. Okay. I was just talking with Ralph this morning, and I saw Jay over the weekend. So, all right. Has anybody else not gone yet? Because then we're going to get into the real meat. Now that everybody knows everybody.
So I haven't gone yet.
Okay, take it, Andreas.
So my name is Andreas. I live in Soldotna, Alaska. Have my GMRS license already. Obviously, not much going on that level up here. So I'm just like taking the next step.
Very cool. And I think you win the award for furthest north.
And I had to wake up earliest also.
And you had to wake up earliest, yeah. Is anybody
All right.
else? Oh, there's Nick. Okay. Go ahead, Nick.
Yep. Sorry, I was able to park after dropping off my kids, so I have a few minutes.
They're
I'm
very
in
very
the,
cute in your
Lake Oswego.
they're very cute in your picture, by the way.
They're very quiet in the picture, which is. I'm in the Lake Oswego area, so just south of Portland, Oregon, and kind of got introduced to ham back in high school. The physics teacher there was really into ham, but I wasn't really aware of it until much later on. About 10 years ago, I started doing some disaster response kind of volunteer work, and crept up again, but life got in the way. And so now I'm finally getting into doing the examinations and trying to get for licensing.
Awesome. All right. Has anybody else not gone yet? Nope. Okay. Everybody have their coffee ready?
Mm-hmm.
Okay. You're probably not going to need it, but here we go. Okay. So what we're going to start with is the basis of all of this. So like I said, when I teach the underpinnings of everything that we're doing. So here's what we're going to draw first. All right. Can anybody name this? This is an easy one to start. Poorly drawn circle, right?
Cartesian.
Yes. A poorly drawn circle on an XY plane. So this is our X and Y plane. I know. Sorry. If the last time you did math was in high school, we're going to do math. And in fact, we're going to do a little bit of trigonometry. So what we have here is our XY plane. All right. How many degrees are there in a circle?
360.
360. Okay. And normally when we think of a compass heading starts at north and goes this way. So we have 0 degrees and 90 degrees and et cetera, et cetera, et cetera. Unfortunately, this is not the way that our Cartesian coordinate system works. The way our Cartesian coordinate system works is that our 0 degree line is on the horizontal axis, which is the x and the positive, in particular, the positive x-axis. So this would be negative x, this would be positive y, and this is negative y. And when we go around the circle and change angles, we go this way. Don't ask me why it's counterclockwise, but it's counterclockwise. So we start at 0 degrees, we come around to the 90 degree mark, we keep going, we're at 180 degrees, and then we keep going and we are at 270 degrees. So when we get back to this point right here, that actually has a name. We're at 360 degrees. What is its other name? 0 degrees.
Well, 0 or 2 pi or cap.
Right. So, but we went all the way around and we're right back where we started. So this is actually really important because we basically have any angle on this particular chart has an infinite number of names. Like we can take 45 degrees right here, and that can also be 405, which means we went all the way around and then kept going. Or it can also be negative 315 degrees, because we could have gone this way, and negative angles work too. The key is that really we usually just call an angle by where it is on the circle, independent of how many times we wrapped around to get there. But it's important to remember that, you know, basically a circle, because it goes around and around and around continuously, we have an infinite number of names for any particular spot. Okay, so there's another fundamental part of a circle. If I were to draw this distance, that has a name. What is that? What is that name, everybody?
It's the radius, right?
That is the radius of a circle. That is how far we are on the point of, on any point on the circle to the center. So, if we were to take this circle, the circle actually consists of all points in space that are the exact same distance away from the center. If I drew this right, which obviously it's not that clean, so I didn't. But, you know, we'll go with that anyway. We'll imagine that I drew it right. And I see a hand up.
Scott, go ahead and finish this because I have a question about what you talked about just before the radius. Finish the radius and then I have a clarifying question.
No, go ahead and ask.
So with the 45 degree or the 415 or the negative 360, if I'm understanding what you're saying is we're going to go with the simplest way to describe it.
Yep.
Don't make it complicated. Go with the KISS idea.
Correct.
Of keeping it simple. If it's 45, just call it 45.
Correct.
Correct?
Yep.
Okay, perfect. Thank you.
Okay. All right. So now, once we have this circle, we can do a couple of things. We can say, okay, well, we have this radius. We'll use the letter R for it. We also know that we have this angle, which we'll use the Greek letter theta for. Now, the question is, there's a couple of ways to describe this point on this circle right there. Well, we can describe it as R that's gone through an angle theta, right? Because we started at a radius, which was right here, down here on the circle base. That was at 0 degrees, and now we've rotated that point 45 degrees in this particular case. So we can say that it's 45 degrees. So that point is R angle 45. So let's say that this is a circle with a radius of 1. Right? That's known as our unit circle. So we now have 1 angle of 45 degrees. That describes that point. So it's a radius 1 with an angle of 45 degrees. Now, there's another way to talk about this particular spot. We can say, okay, we're going to convert our radius and angle, this is known as polar coordinates. We're going to convert this to Cartesian. Cartesian coordinates are x and y. So we can say that this point, this is kind of like looking at a map. In order to get there, we went this far distance x and this far distance perpendicular to it, straight up, a distance y. And in order to get here, we had to go a certain distance x followed by a certain distance y. Now, similar, we could also go up and over to get there. And that would be a certain distance y and a certain distance x, but by convention, we go x over and y up. So there are two different functions that are defined in trigonometry that allow us to do this. This is called the cosine, that is the x component, and the sine is the y component. And these are defined by the angles that we're messing with. And this goes back to the fact that by the Pythagorean theorem, looking at any right triangle, notice this is a right triangle in there, x squared plus y squared equals r squared, where r is that. If we've defined the r as a value of 1, we have x squared plus y squared equals 1. Which means that if the x is cosine of the angle, and we have sine, theta is equal to 1, we know that, okay, well, we have a very important function here, where the cosine squared plus the sine squared equals 1, which is just basically the Pythagorean theorem for this. So now the next thing is that by definition, the sine is equal to x divided by r. So whatever this x is, divided by the radius. Sorry, that's a cosine. And then a sine is equal to y divided by r. So we can do this mathematically and say, okay, well, by measuring these things, we can actually say, okay, for a 45-degree angle, we know that cosine is equal to square root of 2 over 2, and the sine is also equal to the square root of 2 over 2, which is equal to 0.707, 0.707. So what we're now going to do is take these, and I'm going to erase all the ugly math stuff so I can start with a nice clean slate. So now that we have all this cosine and sine stuff, and what we're now going to do is take this and we're going to draw a new graph, and we're going to say that this is now our angle, and this is now our x component. And then we're going to have another one, which is this, which is the angle, and this is our y component. Okay, so what we're going to imagine is that we're going to start at angle 0, and then we're going to go to 90 degrees, and 180, and 270, and 360. And we'll do the same thing over here, 0, 90, 180, 270, and 360. Okay, and here we go. So now we're going to look at this x component. So the plus x is over here on the right-hand side of the graph. When the angle is 0, how far in the x direction are we from the center point? All right, everybody, what is it?
77.
Nope. When we're just laying flat down on the axis, how far in the x direction are we?
1 unit.
We're 1 unit. That's right. We're 1 unit over. Okay. How about when we're way up top? If we look at how far we are in the x direction when we're sitting up top. We're at the 0 point.
We're 0 for
Yep. Okay. How about when we're way over here at 180 degrees?
Question.
I heard a question.
That's back in Chicago. On your red diagram here that you started, you just move the X to the top of the page.
Mm-hmm.
And on the circle diagram on the left, the
Ignore that. We're just making a graph. We're just making a graph. It's a graph of X versus the angle. So as we advance the angle, we just want to know what happens to our X value. So we're only looking at how far over from the vertical axis we are.
Okay.
You'll see in a second.
The X-axis is never going to change, are you?
The X, sure, because the X is how far left and right we've gone. As we start right on this point right here, and we go around.
Go like this.
So if we start right here on the right-hand side, we are starting 1 unit right of the x-axis, or of the vertical line, which means we are 1 unit up, or 1 unit over. When we get to the 90-degree mark, we are now on the vertical line. So our horizontal displacement is now at 0. How about when we're over here at 180 on the left-hand side?
The horizontal is still 0.
No, compared to the vertical
It would
axis.
be 1 unit down.
We're 1 unit left of the vertical line, right?
Yeah, but we're back to the same horizontal line, right? Because if we started at 0, right? All count starts at 0.
But we want to know how far left or right we are of the vertical line. So when we're over here,
we're actually at 180.
-1 unit.
That's right. We're -1. So we are actually 1 unit left of the vertical line. So our point is down here. How about when we're at 270? We're at the bottom. We are on the vertical line, right?
So would that be -2?
No. Well, how far left or right of the vertical line are we?
0.
We're at 0. We're right on the vertical line. Okay. How about when we're back at 360? 360 is also called
0.
0, right? And now we're 1 unit right of the vertical line. So we put 1 unit right. And now we have to play connect the dots. And we know that as the angle changes, it does not follow a straight line. It goes like this. It makes a curve. And now we're going to do the same thing for the one on the bottom. So now we're looking at our y displacement, which is how far above or below the horizontal line we are. So here's the horizontal line. Our starting point is all the way on the right. So what's our how far up or down? What's our elevation at the 0 angle mark?
Still 0.
Still 0. Okay. How about when we get up to the top of the circle?
1.
That's 1. How about when we get to the left-hand side?
2.
No. How far up or down are we?
0.
We're at 0 again. We're right where we started. How about when we're down here at the bottom?
-1.
-1. And how about when we're back at the starting point?
0, 0.
0 again. Connect the dots. Okay. These two curves, which we have now just drawn, have names. What the bottom one we're very familiar with. What's this? What is this called? That's a sine wave. And the one on top?
Cosine.
A cosine wave. And you'll note that, remember we had a sine is equal to the y displacement, and the cosine is equal to the x displacement. How far up and over we go. Those are sine and cosine. Well, if we plot it out, what it ends up being is that the cosine and the sine are just basically unwrapped circles. If you picture just how far up or down or side to side you go, you're basically just taking a circle and you're unrolling it. So these waves are basically just unrolled circles. Now, the nice thing about these is there a beginning or an end to either of these?
No.
There is
No.
not. And why not?
Because a circle is forever.
Circle goes around and around and around and around. So we could actually say that we're just looking at a particular spot, a particular set of angles. But in fact, what we're looking at is the fact that these go on forever and ever and ever. So what do you notice is very similar about these? If I were to take this one and shift it 90 degrees, what do I get?
The other way.
You get the other one. Yeah, you get the other one. So really, these things are basically the same, but they're shifted by 90 degrees. And actually, since we're talking about x and y, you can see that this angle right here is in fact 90 degrees. So essentially what we're looking at is the fact that now we have a circle which we've unwrapped, and we've gotten two fundamental graphs, which we're going to use for a very, very long time now. Because, as it turns out, many, many things in the world, in the universe, go around in circles. And waves, sine waves in particular, are really common. Not everything is a sine wave, but a lot of things are sine waves. So now, once we have this, what we can say is, now that we have a sine wave and a cosine wave, we're pretty much going to ignore the cosine wave, because sine wave is what everybody's more familiar with. It's what people are used to talking about, and you can start with one and just move it and get the other one. So we deal with something called a sine wave. So what we're going to do now is I'm going to redraw this now hideous looking circle. And I am going to draw this in a way that it is not covered with as much garbage. And here's our nice clean circle. Okay, here's our 0 point again. Now, what are some things that I can do with this circle? We originally said that the radius was equal to what?
1.
1. Okay, what could I do to make this circle different?
You could make the radius larger.
I could
or
make it
smaller.
bigger. Yeah, I could make a bigger circle. I could also make a smaller circle. Well, what does that do if I change the radius?
The frequency changes.
No. If I were to draw this curve,
Size of the radius.
yeah, the radius of the circle
The
changes.
amplitude goes
The
up.
waves get closer together.
They do not get closer together.
No?
Nope.
Wider.
Did I say anything about about how fast we're going around? I did not.
No.
So what would happen if I went with a bigger circle? If I went with a bigger circle, I would get this.
Longer to go around.
Change the amplitude.
The amplitude gets higher and longer.
Yep, the circle gets physically bigger. Okay, and I could draw the blue one, and the blue one would look like this. Because the blue one is a lot smaller. That's known as amplitude. Okay, now the other thing I can do is I can decide that whatever speed that I am going around the circle, like this, I could do what with it?
Change the frequency.
I could change the speed, right? So I could, what if I doubled it? What would happen to my graph?
The waves get closer together by half.
That's right. So instead of the green line, for instance, I would now be looking at this. I'd now have this yellow line. What have I done by doing that? I've changed what part of it?
Length.
I've changed the length, and what else?
The amplitude.
No. I've changed the wavelength.
You changed.
And I've changed the frequency. So just by...
Well, if you change the frequency, you change the...
That's right. Well, the frequency is one thing. What we're going to do now is we're going to mess with something else too, because they're all tied together. So now what we're going to do is we're going to say, okay, we have this wave, right? And this wave from the time, oops, didn't mean to do that. From the time we start till the time we make one full pattern, if we were to draw it, this is known as a wavelength. But we have to actually say that this is something real, right? This doesn't make any real sense. I mean, we can say that the wavelength is 360 degrees, but that doesn't really make any sense because that's always going to be true. So now what we're going to do is we're going to take this thing that's sitting on this dot, that's sitting on the dot that's going around the circle, and we're actually going to physically make it move through space. And as it's moving through space, this whole circle is kind of moving through space. So we're going to draw this like this, edge on, like that. So this is now a circle, but the whole circle is going to be moving through space. So if I were to draw this dot goes around and around and around and around. If we were looking at this circle edge on, just like this, how fast would this be traveling? It would be going up and down and up and down and up and down. But would it be moving side to side if I didn't give it any side to side movement? And the answer is no. What we would see is just something that looks like this. It makes a vertical line, up, down, kind of like if I took this, if I took my light and I went like this. Is there any side to side motion here?
No.
Nope, no side to side motion. Now, what if I continue? Go ahead, go ahead,
Doesn't
Vic.
our diagram sometimes look like a slinky that's been stretched out? So it's going around and around, but it's following a tube and moving in one direction or the other?
Yep. Okay, so now we're going to take this and move it up and down. But now I'm going to move it to my right. Here we go. What did I just make? I'll do it again.
Sine wave.
That's actually a sine wave. If I did it right, that's actually a sine wave. But what did I have to do in order to make this a physical thing? I had to physically move my hand from side to side. I had to give it something called velocity or speed. So now what we have is we have this thing that's going around a circle, and it's got a frequency and an amplitude, which is right here. And we have an amplitude. But now we also have this velocity, which is how fast it's moving from side to side. So it's kind of complex movement. You have something that's going around a circle, and the frequency with which it does that is measured in units per second. And that has a name, which is known as a hertz. Amplitude, that could be anything. That could be that could be measured in, that could be measured in just about any units. So it's kind of arbitrary. But the other one is velocity. Now, this could be measured in millimeters per year, right? That's a velocity, a distance in a unit time. It could be millimeters per year. It could be meters per day. It could be, this is my favorite, furlongs per fortnight. I heard that once and thought it was great. A furlong per fortnight. That's a speed, right? It's a distance divided by a time. That's a speed. A furlong per fortnight. Not very practical, but it's a velocity. The one that we usually use by the metric system is meters per second, because a meter is a unit of the MKS system and a second is the basis of time. Go ahead, Sarah.
Yeah. Velocity and speed. Are we ignoring the direction of velocity for now?
Yeah.
Okay. Thanks.
Yeah, we're ignoring the velocity. We're ignoring the fact that it's a vector.
Okay. Thank you.
Okay. So velocity is measured usually in meters per second, and hertz, which is a frequency, which is how many times the thing goes around every second, is measured in a units per second, or sometimes we can put revolutions per second. It's basically a thing per second. So, for instance, if I were to take my hand and snap, that's roughly 1 snap per second, right? So, what would my frequency be?
One
cycle.
One thing per second, right? How about if I went and got my hand tired? That's about two snaps per second, which would be a frequency of
half cycle.
Well, it'd be two snaps per second. Now, what you brought up there, let's say if I had 2 things per second, that's a frequency. That we use the letter F. Okay? Now, I could flip this over and make this something called a T, which is a period. That is the amount of time needed for one thing to happen. T is equal to 1 divided by the frequency, which in this case is 1/2. And this is still things per second, and that then goes to the top, so it's 1/2 of a second. That would be the period. Those are inverse. Period and frequency are inverse of each other. Okay, and if I could...
I'm sorry, inverse meaning?
Divided by. So if I have a frequency, if I had a frequency of 100 per second, right, then I would have 1 over 100. Sorry, 1 divided by 100. That would, okay, so if this is my frequency, then my period would be just divided by. "100 units per second gives me a period. In other words, the time needed for one thing to happen would be the inverse. So it would be 1 over 100. If I had a frequency of 1,000 hertz, my period would be, anyone?
1 over 1,000.
1 over 1,000 seconds, which is also known as 1 millisecond. There you go. If I instead had 1,000,000 hertz, then my frequency, then my period would be
1 microsecond.
1 microsecond. Oops. Yep. We're just keeping track of our, because it's 1 divided by second.
What does T stand for, Scott?
T is period. It's literally a time period. And frequency is going to be in hertz. Okay, now that we have a frequency, and that's measured in units per second, we also have this thing called velocity, which is in meters per second. What do you guys notice about those things? What do they have in common?
They all give me a headache.
No, right here. What unit do they have both in common?
1.
The cycle is
I hear you keep saying the word second, so I'm going to say that's the
They're
common.
seconds. That's right. They both have a unit of time. Okay, so if they both have a unit of time, what we can do is we can somehow combine them. So let's say that we have something that's in a unit of time, right? So we have a frequency in hertz, and we'll say that it's 100. Let's say 1,000 hertz, which is also known as 1,000 cycles per second, and we have a velocity of something that's happening that is 1,000 meters per second. Well, could we divide one by the other and then the seconds kind of go away? It's math. We can do what we want. We can do whatever we want. We can do whatever we want in math. So we're going to have this thing, and we're going to say that it is 1,000 meters per second divided by 1,000 hertz, which is 1,000 meters per second divided by 1,000 cycles per second. Come back. Okay, so the seconds cancel. And now what do we have? We have this question mark is equal to 1,000 divided by 1,000 is what?
1.
1.
1.
And now we're left with meters divided by cycle. Okay. Well, if we were to draw this wave, what would one full cycle be? What is one full cycle of this sine wave?
You
1
start at
second.
the midline, go up, go down, cross the midline, back
Yep.
up to where the midline
Right.
is. So you're
This is
back to the
that
same
is
line
one
you started.
full cycle. Well, if we now know that at this particular speed of 1,000, and we end up with 1 meter per cycle at that particular frequency, F is equal to 1,000 hertz, and our velocity is equal to 1,000 meters per second. What does that look like? 1 meter per cycle. That has a name, a distance per cycle. This has this is the definition of a wavelength. That is a physical distance, and we give this the Greek letter lambda, and it's usually measured in meters. So right here we have, if we have a frequency and a velocity, we have something that links them together, which is this wavelength. And what is really important about this is that, okay, so we have our wavelength is equal to, because we divided them, frequency divided by velocity. We can rearrange this and say, let me make sure I got it right. And okay, I want to make sure I did it right. Meters per cycle. And okay. Velocity divided by frequency. Whoops, I did it backwards. Yep, that's why I had to check. Okay, lambda is equal to velocity divided by frequency. There we go. That looks better. And then we can rearrange this and say that V is equal to F times lambda. This is going to be one of the most fundamental things that we come out of for this entire class. V is equal to F times lambda. So what we can do now is take this right here and erase everything else. So that is what I'm now going to do. I'm just going to draw it right back up here. V is equal to F times lambda. Velocity, V, is measured in meters per second. F is frequency, cycles per second, or a thing per second. And a distance, that's a wavelength, is measured in meters. So velocity is equal to frequency times wavelength. So why is this so important? Let's hear some guesses as to why this is so important.
Figuring the length of an antenna.
Figuring the length of an antenna. What else?
Well, velocity is always going to be constant, right? Velocity is always going to be the speed of light.
It is not always going to be the speed of light. That's also really important to note. Yes. Jared, you said something.
I was saying that this is going to help you figure out what you're transmitting, what the frequency you're transmitting.
Yep.
So if you understand what your wavelength is, then you understand what kind of antenna and what kind of propagation and etc.
And spacing of things and how far in different media things travel. So what we're going to do first is we're going to say, okay, well, let's take a look at sound waves. Sound waves at sea level have a velocity of about 1,100 feet per second, which is about 300 meters per second. That's sound. Sound at sea level is actually pretty slow. So let's say that you hear a note. So this is our velocity. Frequency is equal to, let's say it's 600 hertz. Okay, and we're going to use the formula. We have our velocity. We have our frequency. We don't know our wavelength. So I like to draw this in a circle. V is equal to F lambda, like this. And I cross out the one that I don't know. Notice I'm left with a division bar. So I can say that lambda is equal to V divided by F, which is equal to 300 divided by 600 equals, somebody?
Half.
A half of a meter.
1/2.
So that is the physical wavelength of a tone, 600 hertz, as it is traveling through the air. That is the physical length of a sound wave. Now, why is this important? Do we have any musicians? Anyone ever played a...
Quick question before...
Yeah.
Quick question. What is the letters that you have after the half?
Oh, sorry, that's a meter.
Is that a U and a...
No, sorry, that's a meter.
That's a meter. Okay.
There we go.
Nope. Perfect. Thank you.
Okay. So why is this important? For those of you who have played either an oboe or a flute or a clarinet or a trombone or anything like that, why is this important? Or if anyone ever plays a pipe organ.
Beats per second?
What in particular do we have there?
Distance.
We have a distance. If you have a musical instrument, this is how you tune your musical
Time of the
instrument.
note.
This is how you tune your musical instrument to a note, right? It physically is made by a column of air. So very importantly, let's say that you have a column, you're playing a pipe organ, and it's a ½ meter long. At sea level, you're going to get that tone out of it. So what if you find that the tone that you get is actually 610 hertz and you're sharp? What does that mean about your pipe?
You got to shorten it.
No,
lengthen.
you have to lengthen it. The pitch is too high. So how do you do that? You add something to it and you lengthen the pipe. Just slightly. if you find that instead, once you've lengthened it, it's 595 hertz, what does that mean? That you made it a little bit too long and you have to trim it down a little bit. So then you go and you make your minor adjustment. Okay, so what does this have to do anything with radio waves, right? I mean, what does this have to do anything with radio waves?
The antenna length.
Yeah, okay, so here we go. So V is equal to F lambda. So now we're going to get into this thing called electromagnetics. Okay, so electromagnetics, notice it has electro and magnetic. So if we take this away, it's a combination of electrical things and magnetic things, and we can make a wave out of this. Now, what happens is we have, if everybody holds up your right hand, you'll stick out your thumb, stick out your index finger, and then stick out your middle finger so that they're all perpendicular to each other. They're all making right angles. So you cannot have an electromagnetic wave that has only an electric field or only a magnetic field. Your thumb is the electric field direction, your index finger is the magnetic field direction, and your middle finger is the direction of movement of the entire thing. So it looks like this. You can actually do it. So if I go up, and by the way, this is engineering school. This is what they teach us in engineering school. It's called the right hand rule, and this defines if you're taking an exam, if you're ever in an exam with a classroom full of engineering students and they're trying to figure out how to draw something, they will be, like I was, in class doing this and turning their hand up and down trying to figure it out. So electric field, magnetic field, and direction. So as my electric field goes up and down and up and down and up and down, the magnetic field will be perpendicular to it, like this. And the whole thing will be moving this direction, to the right.
Rod, is that a number 4 down there at the bottom?
That's a letter H.
H.
Yep. It's the
letter
H
H.
field, or yeah, H is the magnetic field. And S is the direction of movement. So electric field, magnetic field, and direction of movement. It's actually, the S is actually known as the pointing vector. It's actually P-O-Y-N-T-I-N-G, but it's really which direction the thing is pointing. This was a guy's name, so it just happens to be conveniently named for something we can remember. So
which one goes to which finger again? One more time, please.
E, H, okay, electric, magnetic, direction. Electric is the thumb. And if you try this out, you'll see that it does not work with the left hand because the left hand is backwards. Your index finger will be pointing the wrong way. So don't do it if you're left-handed. I'm sorry, don't do it with the left hand. Okay, so now what we have is this thing called an electromagnetic wave. And as this travels through space, interestingly, an electromagnetic wave does not require a medium. The thing that we use, which is called Ethernet, the ether was the stuff that was supposed to be in space. Because can a sound wave travel through empty space? Everyone?
No.
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 But an electromagnetic wave does. Electromagnetic wave travels through empty space. So it was assumed that at some point there had to be something which they hadn't been able to discover, and it was going to be called the ether. That was a medium that allowed electromagnetic waves to travel. Right? It had to be, because you can't have something going through nothing. That's not possible. But it turns out that you actually can. Electromagnetic waves do not require a medium to travel. And it's a damn good thing, because otherwise we would be a very dark planet, right? Sunlight would never get here, right? That heat that we require, all that light that we like when we look outside, those are electromagnetic waves. And if those couldn't travel through empty space, our planet would be cold and dark. So it's a good thing that it works that way. So now the question is, how fast, because they're traveling, how fast do these electromagnetic waves travel? Well, in order to do this, I'm going to draw a continuum. We know that all waves have they have several different components. What's that letter F again?
Frequency.
Frequency. And they have this thing called Greek letter lambda. We measure it in meters. That's our wavelength. And these are tied together into something called a V, which is measured in meters per second,
Velocity.
which is a velocity. Okay, those are three things that combine all waves together. So since we have V is equal to F lambda, if we keep our velocity constant, right, we're just going to say that we're just going to keep our velocity constant. What happens if we increase our frequency? What happens if our frequency goes up and let's say that this just equals, 1. If our frequency goes up, what happens to our wavelength?
It goes down.
It has to go down. If our frequency goes down, what happens to our wavelength?
Goes up.
It must go up. Okay. So these are inversely related. If one goes up, the other one goes down for a constant velocity. Now, we do fortunately have a largely constant velocity. So if I were to draw this continuum and I put radio down here and I can put microwaves right here and I can put IR and then over here I can put UV and then I can put X-rays and then I can have a red and a yellow, green, blue, or green, like that. What is that called right in there, that nice little colorful area?
Color spectrum.
That is our color spectrum, which is nice because it allows us to see different colors because our eyes are very good at picking out different colors. All of these are different forms of electromagnetic energy. So how do they vary? What's different between radio waves and microwaves and infrared and visible light and ultraviolet and X-rays? What's the only real difference?
Frequency.
The frequency. The frequency, and because the frequency, what else?
The wavelength.
The wavelength. So radio waves are very long and X-rays are very short. Now, it also turns out that the longer the wavelength, the lower the frequency, these also have very low energy. And short wavelengths have very high energy. And this actually gave rise to something called the photovoltaic effect. This is how solar panels work. This is why if you want to bust, let's say we have an atom here with a bunch of electrons flying around it. If you take red light and you shine it at this atom, nothing happens. And you increase the amplitude of that red light by a factor of 1 billion, nothing will happen to the atom. However, if you take that light instead and you shine an X-ray at it, or purple light, all of a sudden you have an electron jump out. And that's because higher frequencies have much higher energy. So by looking at this, we can see that radio waves have very low energy compared to visible light, and X-rays have very, very high energy. This actually is really important because this actually means that radio waves are a lot safer to use than X-rays, which we know. I mean, you go to the doctor and you don't want to receive 1,000 X-rays at one time, right? X-rays are known as ionizing radiation because they have enough energy to knock electrons apart, to knock electrons off of their atoms and damage DNA, whereas radio waves don't. Now, it is also true that microwaves fall somewhere in this range right here. We'll put it right there at 2.4 gigahertz. which is 2,400,000,000 hertz, or 2,400,000,000 cycles every second. Well, these are, you would think, okay, well, if you stick your hand in the microwave, you're probably going to have a bad day, and that is true, but that is only true because the structure of water, which is H2O, which looks like this, happens to resonate at that frequency, and it shakes the water molecules, causing them to heat up. So it's not actually causing any genetic damage, but if you stick your hand in a microwave, you'll still have a rough day because your hand will probably, all the water will evaporate out of it, and I don't recommend doing it. So, okay, now we have this thing called V, which is our velocity. Now, we know that since light is an electromagnetic wave, what is the speed of light? It has
186,000 miles per second.
Right, and it has C. We call it C, and it's roughly 2.998 times 10 to the 8th meters per second, or we'll just say 300 million meters per second. This is a very convenient approximation. So, for the sake of radio waves, electromagnetic waves of all kinds in free space, our velocity is the same as 300 million meters per second. So this, what do you notice about that? Does it change for our calculations, or is it always the same? It's always the same. That makes it really easy to do this.
How did it change it?
We will get to that. 300, F, and lambda. This is our circle. And because we don't want to carry all those extra zeros out here, we conveniently make this megahertz. We have an implicit million right there. And since we normally use megahertz anyway, this makes it really easy to calculate. So what we're going to do is now we're going to take, as an example, a wave which has a frequency of 100 million hertz. Okay, so our starting point is now a frequency of 100 million hertz. Here we go. F is equal to 100 million hertz. Or you can say that that's cycles, if you want to prove it to yourself that this works. Cycles every second. That's the same thing. And what's our speed of light?
300 million.
300 million meters per second. So now we're going to have a wavelength. We're going to figure out what this frequency wave carves out as it's traveling through space. Well, we can do our division again, and we can say that obviously this is equal to 300 million meters per second divided by 100 million cycles per second, and we cancel those out, and we have 300 million divided by 100 million, which is
1/3.
300 divided by 100.
3
meters.
3.
So about 10 feet. So a 100 million hertz wave in space, traveling through a vacuum, traveling through empty space, carves out a wavelength of about 3 meters. So if we were to draw that and we were able to measure it, we would find that one full wave carves out a distance of 3 meters, or about 10 feet. Or about 10 feet. Okay, so this is really important. Why is this important? Well, it's important for a lot of reasons. Now, to simplify this again, we could actually look at this 300 F megahertz and lambda in meters, and we can prove that this works, and you don't have to write out all those zeros. What we're going to do is say, okay, we don't know our wavelength, cross it out. What's 300 divided by 100? Everyone? That's 3. Okay, so this circle I find is a really quick and easy way to do things. And for the most part, it works really well. So now somebody asked, when is the speed of light not the speed of light? When is a radio wave different? Okay. And what I can show you is, if you've ever looked into, and everybody can try this. So what we're going to draw is a glass of water. Anyone ever looked into a glass of water? Probably. We don't really give it much thought usually. Right? So we have a straw at an angle in the glass of water. And the straw looks like this. What do you notice about the straw?
It's bent
Deflection.
because
It's
of
bent.
light wave.
But now, when you take the straw out of the water, is it magically bent anymore?
No.
We are so used to seeing this that we don't give it a second thought usually, right? I mean, it bends a fork, it bends a spoon. Why does it do that?
Deflection.
It's the water and the air, different consistency.
Water and the air have different indices of refraction, which are caused by or result in the different speed of electromagnetic waves in different media. So air is different than water. How about through plastic? It's going to be different again. Every material is going to have a slightly different index of refraction. And what that means is, so let's say we have polyethylene, right? Which is PE. So polyethylene, do radio waves travel through polyethylene? Sure, why not? It's plastic. It's plastic. Okay, so we have a section of this that's air and polyethylene. What would be the speed of our wave in air? It's actually very close to a vacuum. So this would be 300 million meters per second. How about when it hits polyethylene?
Gonna slow down.
It's going to slow down because in polyethylene, it's about 200 million meters per second. How about if we have air again over here? It'll speed back up. So if I put a wave in that went like this, it might do this. And when it hits this again, it would curve back up. So the pattern, the direction would actually change because it's moving at a different speed. And because it's at an angle, it'll actually change directions. So very cool stuff. And actually the division of the actual velocity in a material compared to a vacuum is known as something called a velocity factor. And this is actually really important because let's say that we have a piece of wire that is emitting radio waves. So you have radio waves that are traveling off from this wire. And they're traveling into space. But this wire is not just a piece of copper. You've bought wire that is surrounded by something called insulation. Anyone ever seen insulated wire? Insulated wire is a great thing, right? Keeps you from getting electrocuted. So let's say that you buy insulated wire and the energy that you're transmitting down the wire largely travels right around this surface. This is something known as the skin effect. It travels right on the outside. What is it really going through? Is it going through empty space?
The air between the insulation and the wire.
Well, there's no air. The insulation is smashed right up against the wire. So where is your energy starting? It's actually starting inside the insulation. So if this is an insulating material that has a velocity factor, because it's not air, of 0.85, for instance, whatever that happens to be, when you make your wire that's carrying a particular wave, what are you going to note about how fast the waves are traveling? They're going 0.85 times the speed of light, and your wire, if you cut it to the, quote, right length to be one full wavelength long, is going to suddenly be too long. It's actually going to be too long to work properly, in which case you're going to have to trim it. So there's all kinds of cool stuff that happens with electromagnetic waves. And now that we have waves traveling through space, we're going to figure out what to do with them. So we're going to take a break. And I'm going to get to use the bathroom. But before I do that, I'm going to ask if anybody has any questions. Remember I said we were going to teach the theory, right? Go ahead.
I have a story about wires and insulation.
Yeah.
My wife has a little car called a Honda.
Uh-huh.
And one day the air conditioner system didn't work. Not surprisingly, she accused me of pushing the wrong buttons. In my defense, I took it to a mechanic who announced that the wire between the air conditioning unit and the air conditioning control head, which happened to be mounted on opposite fenders inside the car, the wire had been completely chewed through.
Yeah. We had that happen on my father-in-law's car.
My wife pointed out that her first husband was a mechanic, and in 13 years of living with a mechanic, she'd never heard of a wire being chewed through before.
Yeah.
So she asked why that was suddenly an issue now. And the answer is, back in the olden days, insulation was made from petroleum.
That's right.
Nowadays, insulation is made from soybean or soy material.
Uh-huh.
That's what the squirrel, rat, chipmunk, whatever it was.
It's food. Yes.
Wanted to go chew.
Yep.
So we spent hundreds of dollars buying new wire.
Yep.
To those back together.
My father-in-law's car, he gave it to my daughter when he was no longer using it, but it hadn't run in a few months, and many wires in the wiring harnesses had been chewed through because they're soybean-based insulation.
That's why all the cars in my house have.
It costs about $2,000.
That's why all the cars in my house.
Yeah, it costs about $2,000 to rewire everything.
Scott, the symbol that you used when you were talking about the air and then the poly whatever and then back to the air, was that the V for velocity and then the F for frequency?
Well, there's a couple. There's velocity and frequency, and then there's the speed of light. Usually V is equal to C, but then there's also lambda. And lambda.
Right. You had it written down. You said it was called the velocity vector or something. It was just for that one.
It's an N. That's an index of refraction.
Okay.
That comes from the velocity factor.
And is that important for this, or is that just an FYI?
It's just an FYI. It's just something
perfect.
to note that the index of refraction largely comes from the velocity of electromagnetic waves in different media.
Okay, perfect.
But that's also why we have something called Snell's law. Snell's law is if you've ever seen like a prism.
Yeah.
That's why prisms do what they do. Because red, orange, yellow, green, blue, indigo, violet, Roy G. Biv.
Right.
They all have different angles of refraction. So when you shine light into a prism, it basically breaks up at different angles based on the frequency. And that's why a prism can separate light into its component colors. I mean, if your prism was made of air, if your prism was made of air, it wouldn't do any good.
Right.
But glass,
Awesome.
because it has a different index of refraction, it refracts light at different frequencies to different degrees. Perfect. Light is just another form of electromagnetics. So yes, it would also, if you could see it, diffract radio waves.
Okay.
Okay.
And it could separate radio waves, which actually gives me an idea.
Glad I could help.
But it would never work. But it's not practical. The diffraction,
Perfect.
yeah, it would diffract a very small amount. All right, other questions before we take a break?
I have a question, Scott.
Yep.
I really appreciate your focus on theory.
Yep.
I think that's very important for us. On the other hand, you've got in this group of people who are going to maybe take a general test or even a technician test at the end of this week.
Mm-hmm.
All of us have got different levels of theoretical mathematical proficiencies,
Yep.
right? Because of our backgrounds
Yep.
and aptitudes. But one thing that we all share.
Tell me when you want to go.
Oh, go ahead. Keep going, Steve.
What?
No, somebody's mic was open.
So one thing that we all share is that we have a time period as a goal, right? If we've signed up to take the examination on Friday, that's a fixed time between now and then.
Yep.
And it seems to me that there is a point where we need to balance our theoretical focus with the efficiency focus on the exam material.
Mm-hmm.
I know that may sound, kind of base or crass, but I think it's a reality.
Yep, I agree.
Just as an example, to show my perspective, I've read the entire No Nonsense guide for the general exam. And I've also done most of the study questions on the Ham study site.
Mm-hmm.
And so I've got a lot of questions, a lot of points that some of them have to do with memorization, and that's completely on me. Things you've got to memorize, like baud rate for different frequencies and so
Correct.
on, and other examples too. And then there's also the effort that needs to be made to understand concepts that we don't have a lot of background to understand. So I'm just kind of concerned about this idea of efficient time use between now and Friday.
Mm-hmm. Well, I've got 16 hours. So that's how I'm looking at it. We've got 16 class hours. So, I think it's important to, even if you haven't done the theory recently, I think it's important to recover it. But yeah, it's going to accelerate as we go. But this is like, if we don't understand this, you're building on something you don't understand. So I don't want you guys having to build on something that you don't really clearly understand.
I actually like the focus on theory, Scott. It's a good review.
Okay. But you know what I mean?
Mm-hmm.
And that's why I'm like, if you've got any questions as we go, it's a good idea to bring it up.
Yeah, as I said too, when I began talking just a minute ago, I appreciate the theory too, but there's also a concern with the efficiency factor that has to do with time between now and Friday.
Yep. Yeah, my goal is to get there. That is my goal.
Scott?
Yeah.
There is a point of mention it. I like the theory, but I think it'd be helpful to take the theory and condense it down into a practical way to, for instance, how to convert frequency to meters, because there's a lot of questions on the test about that.
Yep, but you should already. But now you know.
That's true, but I don't think you brought it out that it's simply divide 300 by whatever the frequency is, but it's only going to be an approximation.
Yep. Well, by virtue of the fact that you have this now.
True.
I honestly, everybody's different.
But the emphasis should be on this, not on the theory.
I disagree. because that's not
Well,
that's
I
not
know.
that's not what
I'm just mentioning.
yeah, but see, I disagree. I mean, yes, but I mean, I can tell you something, but if you don't understand where it comes from, I mean, that's where I may differ.
You are
from,
correct. It's a practical matter. The theory is extremely helpful.
Yeah, and I mean, and what it does is it gives you the ability to then say, okay, I don't just have this memorized. I understand where it comes from and why it is, and that will serve you much, much better everywhere else. I mean, the goal is, yes, the goal is to get through and pass a tech exam, pass a general exam. But really the goal is to give you a background in understanding where this all goes, why we're doing it in the first place. I can tell you, look, the sky is blue, right? And you look up and you have to believe me, but that doesn't mean you understand why. So, but no, I appreciate what you're saying. So yes,
yeah, Scott, I really appreciate the fact that you are explaining all this. I have technicians in a general, and what I did is I just memorized a bunch of answers and regurgitated them on the test, but I didn't understand why those answers were correct.
Mm-hmm.
And now I'm beginning to understand why and connect the dots. So
Good.
I think this is extremely valuable.
Yeah, and when you go to build an antenna, I mean,
And Scott,
yeah, go ahead.
No, you go ahead.
Well, like let's say when you
And
go
I was
to
gonna say, and as a person who has nothing, this is very helpful. I mean,
Okay.
it's sounds like there's many people on here who already have some level, already part of a club, already have one in their license. As a person who doesn't have any of that, this is awesome and amazing, and part of what I understood the class was for. So
okay.
I
Yeah, I mean-
appreciate your teaching style and everything. So.
Okay, I mean, like when you go and like we're going to go to building antennas, and the question is, when you go to build an antenna, why are we making it a certain length? Why do I have to trim it 6 inches? So, that's why you have to trim it 6 inches. Because it's, it just is what it is. The physics defines it. So. Cool. All right. Well, I'm going to go use the bathroom. So we'll meet back in 5 minutes. All good?
All right.
Okay. So we're not going to start up for a couple minutes. If anybody has any more questions, now's a good time to ask. because clearly I don't mind answering questions.
Yeah, sure. I got a quick question for you, Scott.
Yep.
So when you're talking about wire length and we've got the resistance going through it, is there any nice, simple online calculators to be able to do that?
With regard to which part of it?
So determining length. So like I've got an ICOM 7300 with some wire up in a tree out back, and I can receive good signal, but a couple of times I've let someone try to push the auto tune, or it refuses to auto tune. So I'm guessing that I've got some length issues based off of.
Well, how's it being fed? I mean, is it a dipole? Is it, you got coax going to it, or just a random
coax.
wire? Or okay, and what happens at the end of the coax?
It's connected up to almost looks like an insulated piece. The coax screws in, and then it's got inverted V.
Okay, so you've got it's basically a dipole. You've got equal length legs going off the center conductor and the shield.
Correct.
Okay, how long is it?
I had calculated out. I want to say that I had the wire at like 17 feet divided in half, whatever that ended up being.
Okay, so
I was trying to get on.
So that's a 10-meter half wave.
Yeah.
So I mean, it should largely work on 10
say
meters.
10 meter. I was trying to go for, what is it, 14 megahertz, a 20-meter band?
No, that won't work. That's going to be too short.
Too short. Okay. That's
well,
good to know.
Well, I mean, again, that's exactly why we're doing this. I mean, if we're talking about a dipole is a half wavelength long, right? So, okay, let's pick 14 megahertz. Okay, we're going to use 300 F lambda, like that. So our frequency is 14. So we have lambda is equal to 300 divided by 14, which is roughly 21 meters long. So a half wavelength is going to be 10.5 meters long, which is about 35 feet.
Okay.
There you go. I mean,
Interesting. Yeah, I think
this is why we're studying this. This is why we're in class. That's a half wave. Now, if we look at this, that's about 35 feet.
I think I stopped before I went to half wave.
Yeah. Well, no, you went to a quarter wave, it sounds like. Because if you went to a quarter wave, let's say you're making a vertical, the quarter wave would be about 5.3 meters, which is about 17 feet. And actually, you have to take about 95% of it to deal with. You have to shorten it by 5% to deal with capacitive and end effects and self-inductance of the wire and stuff like that. So really, it's about 16'8" or something like that. So if you were to instead take that antenna and say, okay, friend of mine, let's say you try to you send the auto tuner on 10 meters, you'll probably be just fine. The problem then is, why doesn't it work on 20? And the reason it doesn't work on 20 is that we're going to get to this soon, but what is the current? Remembering the current is the flow of electrons. What's the current right at the end of a wire? What's the current at the end of a wire?
The end is zero?
It's zero. How about at the other end?
Zero.
It also has to be
back and
zero.
forth between the two.
Well, it also has to be zero, right? Okay, so let's say that this is a full half wavelength, right? Well, if it's a half wavelength, the pattern has to be like this. That's actually a perfect antenna. What if it's not long enough to draw that, right? And and the antenna is a quarter wave long. It will get up. It'll get up to a certain point. It'll get up to here.
Your wavelength won't go far enough. Yeah. Okay.
Yeah, well, it will, but the problem is that your maximum current would be way up here. You're never at the point where you're at maximum current, so your impedance at your antenna feed point, which is the letter Z, is equal to hold on. Impedance is equal to V over I, because V is equal to I times Z, and that's your impedance. And since your current is going to be something much less than it should be, your impedance is going to be way too high. Impedance is, impedance instead of resistance is what it's a complex value that indicates how the thing behaves at AC currents, which is what we're going to be doing, after this.
Okay. And
All of this will make sense.
It was.
Go ahead.
Yeah, I got the coax off of a ham radio store, but it was saying it was like 100 feet. Is that something to take into consideration for this as well?
We'll get into that too. Depends on the frequency you're using.
Okay, cool. Thank you.
See, it all works together. All works together. Okay, so now we are going to take that wave that we just did, and we're going to do this with it. Here's the Earth, and here's the sky, and now we're going to do some atmospheric physics, or space physics. And we're going to draw this big glowing ball in the sky, which is hopefully yellowish, and is illuminating us during the daytime. And this is called the sun. Okay, so what are some of the things that come out of the sun, everybody? Not everybody all at once. Come on.
UV rays.
Okay, we got UV. What else?
We got heat.
Protons.
We got infrared. Okay, what else?
X-ray.
X-rays. What else? What else we got coming out of the sun? We got particles. We got stuff. High energy stuff. What else?
Flares.
We got flares. Flares are largely energetic particles, so that's counted in the stuff. We've got X-rays. We've got UV. We've got light. We've got
light.
Yep. We've got infrared. What else? The sun is also a huge radio emitter.
Spectrum.
Yeah, it makes basically
Electrons.
Yeah, and we have electrons coming out. Although I usually consider the electrons part of the stuff. So, we've also got neutrinos and lots of other things. Okay, so the sun is basically just pounding us on Earth with stuff and energy. Fortunately, only a very small fraction of these things actually make it down to the surface. Right? Well, it's a good thing that the light makes it down to the surface because we kind of like having light. And it's a good thing that the heat makes it down to the surface because we like warmth, right? Otherwise, the Earth would be, 320 degrees below zero and not very habitable, at least not by us. So what ends up happening is that the ultraviolet, these are the ones of particular interest to us, the ultraviolet and the X-rays, tend to be filtered out by the atmosphere. Now, you can still get a nasty sunburn, but let me tell you that if the atmosphere were not what it is, you'd get a really bad sunburn. I mean, basically, the ultraviolet and the X-rays coming out of the sun, if the atmosphere were not what it was, would sterilize the planet very quickly, and we would have no life here whatsoever, because these are forms of ionizing radiation. Right? Ionizing radiation. Now, so we now have to talk about atomic physics a little bit. So there are largely two components to our atmosphere. What do we have in our atmosphere, everybody? They make up 99%.
Nitrogen and oxygen.
Nitrogen, N2, and oxygen, O2. Typically diatomic for both. We're just going to take a look at nitrogen atoms. Okay, so nitrogen makes up 78% of the atmosphere. And this is nitrogen. Nitrogen has 7 protons and 7 neutrons, and it has 7 electrons flying around. Protons are positively charged, neutrons are neutral charged, electrons are negative charged. And so these are in orbits. And we're not going to get into the Bohr model of the atom. We could, but there's no reason to at this point. So if we look at the energy of the photons, which are the particles of light, which are coming out of the sun, each of those, ultraviolet and X-rays, can have enough energy to actually transfer one of its one of its quanta of energy. It's basically a packet of energy to one of the electrons in this atom and cause it to fly out, which now we have an unbalanced system here. So now, instead of 7 electrons, we only have 6 electrons flying around in the nitrogen atom. And we have 1 loose electron. Well, okay, so now let's take a look at this nitrogen atom. We have 7 pluses and 6 minuses. So what does that mean for our nitrogen atom? What does that make it?
Cation.
That makes it a
No.
positive
Out of
ion.
balance or unstable.
That's right. That
Positively
gives it a net charge of +1. And the electron that flew out now has a net charge of -1. Now, eventually, because opposites attract, someday this electron might end up finding an atom that has been ionized by the sunlight and recombining, at which point the electron will disappear and will rejoin this atom, and everything will be happy again. This will disappear, and we will be neutral again, and this now goes away, and we just have a neutral nitrogen atom. This also works with oxygen. You can see these different things happening when you look up at the aurora, if you live in a northern clime, and you can see that you basically have shimmering green and red lights. Those are basically ionization of different atoms, largely nitrogen and oxygen. Different colors are different energy levels and different species of atoms. So what ends up happening here is that you end up with ions forming and then disappearing on a continual basis. So now we're going to take this nitrogen atom and we're going to make it right here, and we're going to make it a plus and put an electron right there. And we'll do the same with an oxygen. We'll make it a plus and an electron floating around. Then we'll have another one and another one floating around. There's our electrons. Okay, so we have positively and negatively charged things floating around. Okay, so now what we're going to do is we're going to note that these are electrical things, right? These electrons carry a positive or negative charge. They carry a negative charge, and the ions carry a positive charge. Those are both electrical things. Now we have these waves, which are called what again? Electromagnetic. Well, there's that really important part, electro, right? And as ions move, the definition of current is the movement of electrons from one place to another. Electrons that move make magnetic fields. So obviously there is going to be some kind of interaction between these electromagnetic waves and what they encounter up in space, up in the atmosphere. Our atmosphere ends at about 600 miles up. And there are several very definite layers that exist within the atmosphere. We have the troposphere where we live. The air is really thick here, and as you get higher and higher, it gets thinner and thinner. So you might have the stratosphere up here, which is where you fly airplanes, but the air is actually still really thick. Once you get up above about 50 miles or so, you end up with this thing called the ionosphere. And so this is at about 50 miles up, kind of like the edge of space. And you have some layers called the D layer, the E layer, and the F layer. And it's assumed, I believe the reason they didn't start any lower than D was because they didn't know if they were going to find something lower level than D, so they just started it at D. And actually, F at certain times can split into F1 and F2, which are distinctly different. They have different levels of ionization. Each of these layers absorbs different energy particles from space in different ways. So X-rays might make it, because they have lots of energy. Make sure I'm still there. Hold on. There we go. X-rays might make it all the way down into the D layer. Ultraviolet might make it into the E layer. They all can make it into the F layer. Fortunately, most of them are filtered out. So here's an important distinction. Let us say that it is now nighttime. What happens to those? What happens to those? What happens to that source of ionizing radiation at night?
It goes away, right?
It goes away. Yeah. Well, it disappeared. So now, instead of continually forming new ions and new electrons up there, what is happening at nighttime? Up there in the
The
sky.
ionosphere is going away.
The ionosphere is slowly thinning out. Your ionization is sort of falling apart because these guys, the density is really low, but they might find each other, in which case this is no longer functional to, as part of the ionosphere. Well, you might also have this one goes away. So what happens to that population of ions? It goes down. Well, okay, the sun comes up again. And what happens when the sun comes up?
They reappear again.
They start to reappear. So, very importantly, as the sun makes its transit across the sky, what you'll end up with is directly under where the sun is, you'll have a patch that is really heavily ionized, and it will actually kind of make a trail across the sky, across the Earth, as it makes its transit across the sky. Or as the Earth is spinning underneath the sun, you'll basically have an ionized trail where it's heavier and lighter. And what ends up happening here is that these ion layers in the ionosphere, as they form and then come up and then fall apart, tend to cause different things to happen. So this D layer, for instance, during the day, this actually builds up really fast and it builds up really thick because that's a fairly low level of the atmosphere. So what happens is you get a lot of ionization that forms down there, and below about 10 megahertz or so, what happens is that these waves that are sent up to here, they basically make it up to that point and just die. All the energy just disappears. This is why when we're listening to AM radio, for those of you who have listened to AM radio at night or during the day, AM radio during the day can travel about 25 to 30 miles. And at night, what happens is that this layer completely goes away and it's no longer absorbing energy. It's just passing it through. The energy can then continue on to the upper layers and bounce somewhere else. So instead of 25 to 30 miles, you can do 1,000 miles at night. And that is because AM radio has a frequency of about 1 megahertz. And since this filtering happens at about anything below 10 megahertz, the filter is now gone. It doesn't absorb anything. But again, because the atmosphere is so thick down at those levels, the D layer forms very quickly and comes apart very quickly. So it's literally when the sun's out. It's almost instantaneous. Within a few minutes of sunrise, it forms, and then after a few minutes after sunset, it goes away. Well, now you have this thing called the E layer. The E layer is largely uninteresting except when it's not. The E layer can actually form very dense levels at times of electron clouds. So dense, in fact, that typically, if you think about it, the higher the frequency of a wave that is sent up, typically it requires the higher the frequency, the more intense layers of ionization are required to bounce it. So if I were to take this wave, let me get rid of those. If I were to take this wave at 14 megahertz, there's a good chance that it will bounce. If I were to take the same wave at 28 megahertz, if I don't have enough energy, if I don't have enough ionization up in those layers, it will just pass through into space. Similarly, if I were down at, let's say, 3 megahertz, and it's daytime, and I have the red band of D-layer ionization occurring, this absorbs anything below 10 megahertz, then the yellow, the 3 megahertz energy, would basically disappear. The 14 megahertz energy would suddenly pop up over here. And the 10 meter energy, which is at 28 megahertz, would go off into space. Now, typically, the higher we go, the more severe it is. Let's say that I were on the 2 meter band at 144 megahertz. That's clearly going to go into space, right? If I have this layer of ionization up here, that's enough only to handle 14 megahertz. Then obviously 144 is going to go into space. So the maximum frequency that can work at any given time, this has a name, and it's known as the maximum usable frequency, or MUF. The lowest frequency that can work at any given time is actually known as the LUF, or the LUF, lowest usable frequency. And that usually comes from the low levels of the atmosphere, and the MUF usually comes from the upper levels of the atmosphere. During the day, you have this bifurcation of the F layer into F1 and F2. They form two separate levels. At night, these typically tend to just form into a single F layer. The F layer is what gives us our very long-range propagation. The reason that it does is because if you were to look at this essentially mirror effect way up here in the sky, and this is 375 miles up, well, looking at angles, you can see that if it made it 375 miles up, if this is a 45-degree angle, this is 375 miles, and this is 375 miles, and that all of a sudden is covering a distance of 750 miles. And usually it's a lower angle than that, which stretches it out even further, which is why ionospheric propagation can be so useful, because these skips, as they're called, can cover up to 2,000 to 2,500 miles in one bounce, because we're basically using a mirror effect way up in space.
I can't keep track of them.
Bobby May, you got a question?
No, I can't keep track of you. I can't keep track of where you're going.
What do you want to know? I'll go back and do it again.
No.
Again, this is really important.
It's really hard for me to keep track of where you're drawing, to keep track of what you're talking about.
Okay, so we'll start again.
And Scott, this seems like a really basic question.
Yep.
But the more stuff that's in the ionosphere is when you're getting the bounce, right?
Yep. You basically have a density of electrons, density of ions, and a lot of it depends on where they form and when. So if I have the D and the E and the F, and during the day, so I'm going to put the sun up here, you have the D layer that gets really, really heavily formed because the sunlight is shining ultraviolet and X-rays at it,
Yes.
right? So that becomes very, very dense. If I take my waves and shine them up here at anything below 10 megahertz, what happens is that these basically get in here and they just get absorbed. So this is during the day. If I'm above 10 megahertz, they make it through.
If you have too much power, will it just not skip or bounce off and just keep
It
going?
doesn't matter. I mean, when you say too much power, the atmosphere doesn't care. Physics is physics. So above 10 megahertz will pass through. Now, the problem is, again, what happens is that you end up with these ions that are up here, right? They may be really, really dense, or they may be very sparse. Depending on how much there is up there, that determines the maximum usable frequency.
Chicken kebabs and
Depending on how much ionization is up there, that determines what the maximum usable frequency is.
Okay.
Below the maximum usable frequency, it's below the maximum, so you're going to get a bounce at a certain angle. Above the maximum usable frequency, so this is, oops, below MUF is going to bounce back down. Above MUF is going to go right through. Yep.
Okay.
So the E layer is another layer that can form. And the E layer typically does not work on this stuff, except that it sort of generates a separate path for things that are in the 50 to 200 megahertz range. We'll even say 20 to 200 megahertz. And it can actually form an alternate path with heavy, heavy, heavy layers of ionization in here. But it happens only very occasionally, and the skip zone is like this. It's usually like 1,000 miles. Versus, in the case of long range, it's like 2,500 miles.
Yeah.
Because it's not nearly as high, so the coverage distance is not as good. And this is actually a mode known as sporadic E. And what's interesting about this is that if the maximum usable frequency is 22 megahertz because of the F layer, and I somehow end up with 50 megahertz bouncing off of the sky, well, that's above the maximum usable frequency, isn't it?
Mm-hmm.
50 megahertz is well above that. So this is almost guaranteed to be sporadic E, that it's following some alternate path to get there. So how about, because we're doing the technician and general stuff, right? The technician first, though. So let's say that a technician licensee has privileges at 144 megahertz. So now we're going to use that formula we just calculated. What was it? 300 F and lambda. And we know our frequency is 144. So what's 300 divided by 144, roughly?
A little over 2.
Yep. And what band do we call that?
2 meters.
That's the 2 meter band. So 2 meters will typically just pass right on through. It's actually quite rare that we get any kind of propagation that's caused by 2 meters bouncing around at the upper levels of the atmosphere. It would require so much ionization that typically the sun is not capable of making it.
So if someone broadcasts above the MUF, does anyone hear it, or is it just like?
That's how you talk to space.
Okay.
That's how you talk to satellites. That's why satellites can operate on 144 and 440 megahertz as if there's nothing in the way. Because it's almost guaranteed to pass through everything. That's why we use different microwave frequencies for uplink and downlink. That's why Sirius XM works. Except when it's raining. That's another story. Yeah.
Scott, maximum usable frequency is always changing.
Yep.
How do you calculate that, and how do you know what it is?
It is largely done by looking at the amount of solar radiation, ionizing radiation coming out of the sun. This follows, this varies as the sun turns on its axis. You'll get areas of more sunspots, which generally produce more in the way of stuff, ionizing radiation. It also varies on an 11-year cycle. We're in cycle at the peak, almost at the peak of cycle 25. So there's more ionizing radiation coming out of the sun than there was 5 years ago. So 5 years ago, what would end up happening on field day is that you would hear nothing on 15 meters and nothing on the 10-meter band because there wasn't enough ionizing radiation. This year, 15 meters was great. 10 still wasn't very good, but 20 meters was awesome. And a few years ago, 20 meters was largely dead during the day and completely dead at night. So that's again due to, you have your 11-year cycle. You also have, on top of that, you have the fact that the sun is always, if you want to think about it, in the same place, but the Earth is tipped on its axis. So during our summer, right where we are is tipped right toward the sun. That's why it's hotter during the summer than during the winter. We also get more ionization during the summer. During the winter, it's nighttime for longer and the sun is, further away. It's not as direct, so we get less ionization. And this is visible by looking at actual, let's see, here we go, display reception reports. I'm going to share this. So there's something that we use called PSK Reporter, which is an automated reporting system for digital radio systems. These are high frequency signals that are bouncing off the ionosphere. Notice what's being received in Oregon. These are separated out by frequencies. Well, it's largely 17 meter band, 15 meter band. But now we're going to look at, we'll see how fast it loads. With the world centered on Australia. Okay, so notice the colors of those linkages are completely different. This actually is largely on the 40 meter band. And notice we have virtually nothing between that part of Australia and the United States. Notice what that gray line is, right? Where it's nighttime on one side and daytime on the other.
Mm-hmm.
You get these day-night shifts. It changes frequencies. It changes propagation from day to night. It changes it by season. So let's take a look at, let's say, JN65. Let's see if this comes up. Okay, no, we have a totally mixed bag. Notice all those different colors in Europe, right? We've got some signals going to the East Coast, but none going to the West Coast. They're basically also able to follow on the higher frequencies. Notice those are largely following the pattern of the sunlight, going from Europe to Japan. And even, let's see what band, that's on 15. So now what we're going to look at is we're going to look at whether or not anyone down in the Gulf Coast area has any of these red lines. And, oh, okay. So now we're going to take a look at anyone in Dallas who is using the 6 meter band. The 6 meter band is 50 megahertz. This would be evidence of E-skip or sporadic E. So somebody in Dallas is actually hearing, notice how short the skip is. That's, 800 to 1,000 miles. This is using VHF, which is usually line of sight propagation, to go from Texas to Wisconsin. So these bands all behave differently at different times of day and different frequencies. That is part of the fun. Also, being able to understand that allows you to pick certain frequencies that you're going to use. Let's say you have a target of being able to talk to somebody in a particular place. So what we're going to do is open up one more website. There's so many tools out there right now. It makes it a lot easier. So this is something called VOACAP, which is the Voice of America. If anybody remembers the Voice of America, which was America's voice to the world. One of the things that came out of VOACAP was that there were propagation tools, because it was important to figure out, it was important to be able to pick certain times and paths and frequencies and antenna headings if you want to talk to a certain place. So let's say we want to talk to somebody in Morocco from the West Coast. Short path, and we're going to pick we're going to pick voice. We want to speak to them. We're going to run 100 watts. We have a nominal antenna, and we look at the propagation wheel. The brighter it is, the more likely it is. So this tells you, notice this is 10 meters, 12 meters, 15, 17, 20, 30, 40, 80, 60, 80, using the high frequency bands. And notice around the outside, 0 hours UTC all the way around to 2300. This tells you what band and what time you should try in order to try to succeed. So let's say that you went with an amplifier. Notice it just got easier. Let's say you went with Morse code instead. Whoa, it just got a lot easier. It's a more efficient band, more efficient mode. So many good propagation tools out there.
That's pretty cool.
It is really cool. Okay, so now what we're going to do is we're going to take a look at the book and see just how we did. And so what I'm going to do is, if I can figure out how to do it, we're going to, hopefully everybody has a copy of this. Everybody have a copy of this book?
Yep.
Okay, excellent. So what we're going to do is we're going to go to, I believe we're in the page 20s. I do everything a little bit out of order because I like doing the propagation stuff first. Let's see, propagation, blah, 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 radio wave characteristics, frequencies, and stuff like that. Okay. So, radio wave characteristics. Everybody have this?
What page?
On the, well, it's not numbered, but it's the 39th page of the PDF.
Ah.
And it'll say radio wave characteristics. But what you'll find is cool about this is that if you're studying for the general test, I always cover too much. This is the same stuff that's covered on the general test. You know, the basic fundamental stuff for radio waves is going to apply to both. Okay, everybody there?
No, I can't find it.
Radio wave characteristics.
Got it.
Okay, what are the two components of a radio wave?
On mine, it's on page 35 of the PDF.
Okay. Oh, is it actually, is it numbered?
Well, on my interpretation of it is 35, page 35.
Okay.
There's a page number.
But I think that could be different for different people depending on their reader.
Yeah. Okay, radio wave characteristics. The two components of a radio wave, everybody? It's an electromagnetic wave, so electric and magnetic, okay? And what do you know about electromagnetic waves? If you hold up your right hand, the two components are at right angles. Yep, they're all perpendicular. Okay, the velocity of a radio wave traveling through space?
Speed of light.
Which is roughly 300 million meters a second. Okay, so how do you know how to convert from frequency to wavelength?
What's the easiest way to do it? 300 over frequency.
By weight.
By the frequency.
Yep. So that way, you know, if you see, okay, well, what's the formula for doing that? You can always do it like this. This is why I like the graphic 300 F lambda. Just make that circle and do that, and you'll never forget which one is which. Right? Whichever one you don't know, you have a divider line. So lambda is equal to 300 divided by F. And you never have to guess which one it is. Okay, so share again. Okay, in addition to frequency, what's used to identify amateur radio bands? We call it the 2-meter band. Why do we call it that?
Because that's its wavelength.
That's its approximate wavelength. How about the 15-meter band?
Approximate wavelength.
Approximate wavelength. Okay. All right. So now we have these things called HF, VHF, and UHF. And these are just things that you have to remember. These come from the electromagnetic spectrum because the electromagnetic spectrum is a continuum that goes from frequency, let's say 3, really it goes from 0, up to infinity hertz. And it's separated out in these things called decades. So 300, 3,000, etc. And then we're up to like 3 million. And then there's 3 billion. So this is from 3 megahertz. We're going to get to mega very shortly. That's known as HF. That ends at 30 megahertz. And then from 30 to 300, 30 to 300 is known as VHF. And then from 300 to 3000, which is also, because 3000 megahertz is equal to 3 gigahertz, we're using a different prefix, that's known as UHF. So if anyone remembers having a TV that had VHF and UHF channels,
right,
this is why you had VHF and UHF channels. Because they were in different frequency bands. And in fact, so if I now tell you, now that you have a different view of this, that FM radio, you're listening to 106.7. That's going to be right about there. Because that's in megahertz. How about if you're listening to AM radio and you're listening to 1170 AM? That's actually in kilohertz, which is 1,000. So it's actually 1.170 megahertz. So that is way down here. It's actually in the MF band, which is not something that you have to remember, but it's even below the high frequency band. So now, if I said, could you build an antenna for this? Well, you could certainly figure out the wavelength, right?
Yeah.
If you can figure out the wavelength, you can probably build an antenna. So which antenna is going to be longer? Even though 1170 is bigger than 106.7, is it not?
Yeah.
Yeah, but the whole prefix thing is off by a factor of 1,000. Right? Because it's 1.170 megahertz. It's off by a factor of one wavelength is 100 times longer than the other between AM and FM radio. It makes building an AM/FM radio and antenna very challenging, actually. So the thing that we would call television, channels 2 to 6 were actually down in here. Yeah. Yeah. Okay. So 2 to 6 were down in here, and 7 to 13 were in a different section up here. So those were known as VHF low and VHF high. And then your UHF frequencies, channels 14 to 83, would be way up here. So they were actually separated out into multiple different frequency bands. If you've ever seen a TV antenna that had really long sticks on it and they go down to way shorter sticks, that is so a TV antenna could actually pick up that very, very different range of frequencies and do an okay job at all of them. And that's a special antenna actually known as an LP or a log periodic. Very, very low gain, but very wide bandwidth.
OPB in Portland is still using VHF.
Mm-hmm. Right. Okay, so let's see. We're going to go back to sharing this. Okay, so HF is 3 to 30 megahertz. VHF is 30 to 300. UHF is 300 to 3000. And I will probably ask you that numerous times as we're going. RF is radio frequency. So RF means radio frequency. Okay, so now we're into propagation modes. So why is the radio horizon? Okay, so we're talking about VHF and UHF. Those are much higher frequencies. These are the ones that typically pass right through the atmosphere. If you shoot them along the horizon, what will happen is they will tend to curve on the horizon. And if you've ever been lucky enough to be on the Pacific Ocean and you see the sunset, you notice how the sun looks green for just a split second right before sunset. Has anyone ever seen the green flash? If you've been lucky enough to do that?
I have.
The green flash
Yep.
is when all the other colors of light have been filtered out because they're bent above you. Longer wavelengths tend to be the last ones to disappear. So at radio waves are really long compared to visible light. And what ends up happening is that radio waves curl around the horizon slightly, and more so than the visible, more so than light. So if the horizon is 50 miles away, you may actually be able to operate radio waves for 75, 100 miles. So the atmosphere bends radio waves a little bit. Why are simplex VHF signal or UHF signals rarely heard beyond the horizon? And that is because they're a high enough frequency that they basically just shoot on through. So we can also have a little bit of this happening sometimes. Has anyone ever driven down a hot highway?
Mm-hmm.
When you see the water.
And you see what looks like, right? Here's the roadway.
Garage.
Right? And you see this bluish pool in front of you on a hot day.
Yep.
What is that?
As a kid, I thought it was water.
Yeah. What actually is that?
The sky.
Reflection.
Yeah, but how does it get there? How does it get there?
The reflection of the heat.
Bouncing or propagation of the.
So the easiest way to describe it is, let's say that we have the roadway. Above the roadway, on a really hot day, you get a very, very hot layer of air. Normally, as you go up, right, you end up with a cooler layer up here. Well, as you get these layers of heat, hot and cold, in the air, what happens is their index of refraction changes. Just like, glass, electromagnetic waves travel at a different speed through glass than air. Those waves travel at a different speed through those different temperatures of air. They have different densities. They travel different speeds. They bend a little bit. And what happens is that the skylight, the light from the sun, will come down into here, and it will actually get caught and bounced back and forth. And this is actually known as ducting. So what you're seeing is a reflection of the sky that has been ducted between the layers of air and the roadway. We also get this on the radio. But as you can imagine, because light typically has a wavelength of about 600 nanometers, which is 0.000000600 meters, radio waves are more on the order of, let's say, 10 meters, right? That's a lot of orders of magnitude different. Well, this duct obviously isn't going to fit down there. This duct is going to exist like up in the sky. And this might be at a height of, let's say, 20 miles, 10 miles, where you have a temperature inversion in the atmosphere. So you might suddenly get a warmer layer up here above cold air. And where do you think that might happen? Can you, Yanni, you spend some time on a boat?
Yes.
Where do you think you might see that?
On the sea.
On the sea, because even on a hot day, the air right above the water can be really cold, right? So you can get a nice temperature inversion there. So over the ocean during the summertime, what you often get is this inversion layer. And what can happen is your radio waves, which you will transmit up into them, go like this, and you get bouncing and bouncing and bouncing. And this can actually happen at VHF and UHF, where those radio waves can get trapped in the layer and then ducted and then come out somewhere on the other end. And because this happens in the troposphere, which is where we live, this is known as tropospheric ducting or tropoducting.
You can even see in the distance other ship floating in the air instead of being in the water.
That's right. Yeah, you can see islands in the air sometimes too, if there's an island nearby. It's actually a reflection of the light. So it works, and this is known as ducting, and it works for radio waves as well as a little bit less visible light. And this can allow you to get, normally VHF and UHF, this is, let's say, 144 megahertz. Normally that is line of sight because the atmosphere just sort of like doesn't do anything with it, but sometimes it does. And then you end up being able to cover a distance of, let's say, 300 miles. If you happen to be up on a mountaintop in California and you're aiming it toward Hawaii, and there's somebody on a mountaintop in Hawaii and you're 2,200 miles away, you can actually talk to that person all the way at the other end, let's say using 10 gigahertz through the duct. People do this just because they can. So mountaintop to mountaintop from California to Hawaii during the summer. Okay, so that's known as ducting. Okay, so now we're into why do signal strengths often vary? Okay, so who here has ever used a VHF or UHF radio for work or any other purpose?
I have.
Okay, so have you ever noticed that sometimes you just get in a dead spot?
Yes.
Okay, why do you have a dead spot? What is a dead spot?
The signal can't get through.
Well, maybe, but why? But why is the question? So we're going to draw a wave.
Scatter, maybe.
Yeah. Okay, so we're going to draw a wave. What are some fundamental things about this wave? What does it have that makes it unique?
Dips and tips.
Yeah, but what would we call that? We'd have an
Wave.
amplitude, which is its size, bigness. What else?
Wavelength.
Wavelength. What else?
Frequency.
Frequency, right? Good. Okay. Now, we have an amplitude, a wavelength, and a frequency. The wavelength isn't going to change. The frequency is not going to change. What else is there about this wave?
Phase.
We have
Length.
phase. Yeah, we have something called phase. So if we were to take this wave and we were to shift it in time so that it was like this, we would shifted it forward, or we could actually shift it backwards. Right? In which case it would be a little ahead or a little delayed. That's that shift in time, which we can actually translate to angle, right? Because this is 360 degrees for one full wave. That's known as a phase shift. We've actually changed the phase of the wave, and we can do it like this. Right? So each of these is now 90 degrees of that wave different from the other. So we could say that this one is our 0 reference. This one is 90 degrees behind because it waited 90 degrees to start. And this is 90 degrees ahead. So this one would be lagging, as we'd call it. And this one would be leading from that center one. So now we have established that there's something called phase, right? And that goes back to something going around a circle. So by doing that, what we now have is we have this additional thing to be a little concerned with. So now we're going to draw a wave, and we're going to say that our wavelength is 1 meter long. right? We don't have a 1 meter band in the ham world, but we don't care for the sake of this. Okay, so if I am a distance of 300 meters away from my target, how many 1 meter wavelengths will there be between those 2 points?
300.
300 wavelengths. Okay. So 300 waves. Okay. But now let us say that this radio wave, in the process of getting there, because it also went this way and this way, because nothing's perfect, that there, oh, well, we sent some this way and it found a wall. And that wall bounced this signal so that we have 2 waves getting there that were generated at the same time from the same place. Right? This is a very likely scenario. This is actually called multipath. So now we have the blue wave and the red wave getting there at the same time. So I'm going to draw the red wave. Right? There's our red wave. And let us say that because the blue wave had to go a little bit further, let's say that the blue wave went just a tiny little bit further than the red wave did. When it got to the end, would it be a little bit ahead or delayed?
Delayed.
It'd be delayed just a little bit, right? Well, is that going to add or subtract? And the answer is, I'm not really sure, right? At times they would add together, at times they would subtract from each other. Like where one is plus and one is minus, they'd probably subtract. Where they're at the same place, they're going to add. But let's say that that path that it followed was an entire half of a meter longer. Half of a meter. What is our wavelength? What did we say our wavelength was?
1 meter.
1 meter. Okay, so where would a half of a meter put this delay?
1/2 meter.
Right there. And it would be like this. Now, the amplitude probably wouldn't be the same, but it would be delayed. So what can you say? This is what actually gets to the other end. When one is going up, the other is going
down.
All right, so what would happen to them?
They cancel each other out.
This is known as destructive interference. This is a dead spot. So, how do you fix this? Well, the real problem here is that half meter extra long path that you have, right? So, you could move this way a little bit. You could move this way a little bit. You could move that way a little, maybe that way a little. And because the wavelength is 1 meter long, you wouldn't have to move very far, would you? It might be you move 6 inches or 8 inches one way or the other, and you go from a dead spot to a place where those waves are now in phase with each other and they're adding together instead of subtracting. This is known as multipath. If you're going from an area of constructive to destructive interference and you're in a car and it's happening very quickly, it's known as picket fencing because it sounds like you're talking to somebody through a picket fence as you're walking down the street. They're really loud, then they go away. Then they're really loud, then they go away. Okay. Okay, so what can multipath do? If you're not in a good spot, if you're using digital communications, let's say you have 2 computers talking to each other and the signal because it goes away. If you're using voice, you're not going to be able to hear them as well. If you're using computers, using data transmissions, you might be in a bad spot on Wi-Fi. If you're on a bad spot on Wi-Fi, then your error rates increase and you have more errors occurring, which means that your data rate goes down. If you're using a directional antenna, you can actually take a signal and intentionally bounce it off of something like a building or a mountaintop. I have a friend who was up at Mount Hood. If you're familiar with Mount Hood, it's a big 11,000 foot tall mountain, and he was in the valley to the south of Mount Hood. We live to the south of Mount Hood. In order to talk to us back in Eugene through the repeater, which is to the south of Mount Hood, he aimed his antenna at Mount Hood. and intentionally bounced signals off of this big mountain in front of him. And we were able to hear him. There's an effect called knife edge diffraction, and this comes from the fact that if you have a sharp object, like the top of Mount Hood, for instance, some radio waves will actually diffract as they go over the top, and they'll bend down toward the ground around a sharp object. The effect of vegetation on UHF and microwave signals. Okay, so very important to note. So let's say that I have this box, and it's in my kitchen, and it looks like this, and it has a bunch of buttons and knobs and stuff, and it has a door, and here's a bunch of buttons, and I put my food in it, and my food gets hot. What is this thing called, everyone?
Microwave.
Microwave oven. Now, what if I told you this was actually a 1 kilowatt radio transmitter? Would you believe me?
Yeah.
Okay, so in here you have this thing which is generating 1,000 watts of RF and injecting it through a waveguide into this cavity. So this cavity is now filled with 1,000 watts of radio frequency at 2.4, let's say 2.405 gigahertz. Now, that again happens to be the frequency where you have oxygen and 2 hydrogens, and that is a resonant frequency of H2O. Resonant frequency is such that it causes it to vibrate. So you put energy in at this frequency and it causes water molecules to vibrate. Vibration is motion, and motion has another name in physics. It's known as heat. So by putting 1,000 watts of RF energy at that particular frequency into your microwave oven, you heat up the water and you cook your food. Which is also why if you stick a bagel in there, all the water will boil off and you'll end up with a rock-hard bagel instead of a cooked bagel. So the interesting thing about this is that that resonant frequency of water at about 2.4 gigahertz, what happens if you have a transmitter, for instance? It turns out that 1.4 gigahertz is a legal ham band, believe it or not. We use it for microwaves, we use it for data communications and lots of other stuff, and we can build a horn antenna that looks like this. And we can have a transmitter back here and operating at 2.405 gigahertz. Now, it also turns out this is a Wi-Fi frequency, also known as the 2.4 gigahertz band. So if we were to transmit this signal and try to talk to another something somewhere else, and there's a bunch of, we're going to make it green, there's a bunch of leaves hanging on trees. What do you think would happen to the signal as we tried to pass it through?
Gets absorbed.
It gets absorbed. And all of a sudden, what happens is when there's a lot of trees in between you and somebody else on UHF and microwave frequencies, the closer you get to the resonant frequency of water, the more absorption there is by the vegetation.
Oh, interesting.
HF frequencies don't care. VHF, UHF in particular, and microwaves, it makes a really big difference. Okay, antenna polarization. Okay, well, we haven't really done antennas yet, but I think it's about time to do antennas. So, because we've talked about waves and we've talked about propagation, I think it's time to talk about antennas. Let me just make sure that we're in the right section here. We're not going to do that yet. We're going to do this. We're going to do antennas because I love antennas. Standing wave ratio and antennas and feed lines. Okay. You know what? Let's go do let's do electronics first. Let's get back to that part. Okay. So we're going to get back to antennas in a little bit. But now we're going to talk about, we're going to go back to kind of the beginning where it says electrical principles. So this is basically at the very beginning of the book. It's a good time to talk about Ohm's law, because then that'll work together to give us antennas. Okay, Ohm's law, named after Georg Simon Ohm. He was a scientist in the 1800s, and he figured out that there were these things called electrons. An electron is a charged particle, very, very tiny, and that if you took a something, we'll call it a piece of wire, and you applied a volt, which is a unit of electromotive force, which is the ability to move electrons through something, then you would have a current that would flow. Current is known as an ampere, which is actually 1 coulomb of electrons every second, which is an enormous number of electrons because electrons are really tiny. The ability of this thing that you're trying to pass those electrons through, to resist the flow of electrons is known as an ohm, named after himself, Georg Simon Ohm. So we have Ohm's law, which is this thing called electromotive force, which is the push is equal to the current that flows times the resistance. So basically, this means the harder you push, if you have a constant resistance, you will have more electrons moving. E is equal to I times R. This is Ohm's law. And we can write this out in the same way. E is equal to I times R. The only difference being that if we don't know, for instance, the E, if we don't know the E, then this is I times R.
Multiply.
Yep, you multiply it. Otherwise, you have a divisor bar and you leave that. So if you have your current, if you don't know your current, you have E divided by R. So a very convenient way of remembering it. I've seen it done like this with a triangle. I personally like the circle. So, okay. So now we have Ohm's law. All right. So we have this thing called an electron, which is a charged particle. Again, electrons are really tiny, and they have a very, very small but not zero charge. They are negatively charged. And what we have is our nucleus of our atom, which has protons and neutrons in it. And then flying around the nucleus in different orbits, we have electrons. So some materials, when we push an electron into the material, are very easy to shove an electron into, which will flow and push an electron back out. If we line up a whole bunch of these in order, what we find is that some materials are very conducive and very easy to being able to have an electron shoved into one end and come out the other end. You can line up a whole bunch of them, and it doesn't really care. If you put one electron in, you get one electron out. This is the flow of electrons, which is known as current. And this is measured in amperes. And this is given the letter I for an impulse, because ampere was French. It's actually an ampere. The amount of push that you have shoving this electron in is an electromotive force known as E, and this is measured in volts, named after Alessandro Volta, who was another 1800s scientist, worked with electricity. That is given the big letter V. The ability of this material in between, whatever it happens to be, to resist the flow of a constant stream of electrons is known as resistance. That's the big letter R. This is measured in ohms given the sign omega. So again, E is equal to I times R. We sometimes might write this if we're writing things in. So let's say we have a circuit and we measured our voltage at 10 volts and we measured our current at 1 ampere. And by Ohm's law, E is equal to I times R. Well, E is our electromotive force, which is our volts. Current is our 1 amp. So we don't know our resistance. So the question might be, what is the resistance? We don't know this. R is equal to E divided by I. It's equal to 10 volts over 1 amp, which is 10 ohms. So that is the resistance of our material, whatever that material happens to be. If it's a black box, it's just a black box. We just know that this is for a constant stream of electrons. This is the resistance. A constant stream of electrons always flowing in one direction is known as direct current. If it goes back and forth, opposite directions, that's known as AC. If it's always flowing in the same direction, that's known as DC, or direct current. AC always changes direction. So, if we look in our wall socket, I'm going to cancel my share here. Let me make sure I got my camera on. Everybody see that wall socket down there?
Yep.
Okay. That is how many volts and what kind of current?
120 volts. It's alternating current.
And it's 120 volts. And it's alternating current. Which means that if we were to draw the voltage in time, it would go like this. It would be a sine wave. And actually, as it turns out, it would actually, if you were to measure it, like on an oscilloscope, which you can use to observe the wave, observe voltages, it would actually go to 170 volts and negative 170 volts. But you would have
0.707.
Yeah, 0.707. That's right. And what would be the frequency of that wave?
60 hertz.
That would be 60 hertz. Okay. Okay. So how about if you were in Europe?
50 hertz.
And also, what would your voltage be?
220 mostly.
220 and 50 hertz. So different voltage, different current. Okay. So now that we have looked at that, let us say that we don't have that voltage anymore. We have this voltage. We have a little box with a terminal on the top, two terminals, and we have a plus and a minus. That might look like a little bit like a 9-volt battery. What would be the voltage of that?
DC.
And what voltage if it's a 9-volt battery?
9.
9 volts DC. You could also get a cylindrical battery that looks like this with a knob on top. That would be a D-cell battery. And what's the voltage of that?
1.5.
1.5 volts, AC or DC?
DC.
That would be DC. In other words, the current always flows in the same direction out of this. Now, this is actually really important. We're just going to say it once. If I were to take this battery, and I'm going to draw it like this. Here's my battery. This is drawn as the positive terminal. This is drawn as the negative terminal. By convention, we're drawing a basic circuit. This comes from the word circle. This is our resistor. That's the schematic formula. That's a schematic for a resistor. And let's say this is a 10-volt DC battery. Notice this is actually a battery. It has plates. By convention, this is the plus and this is the minus. A resistor does not care which direction electrons are flowing through it. Let's say that this is 10 ohms. Okay? Well, we have E is equal to I times R. I can do it in the circle as well. EIR like that. And I don't know my current. My current would be flowing around, because current is the flow of electrons through a piece of wire or through a thing. I don't know my current. I is equal to E divided by R, which is equal to 10 divided by 10 is 1 amp. Okay, which direction would it be flowing? Always the same way, right? I said this is a DC current source, right? And it would always be flowing in the direction of the arrow. But now I'm going to ask a question. What are electrons, plus or minus?
Minus.
Minus. So which way are the electrons actually moving?
Minus the plus.
The other way.
The electrons are actually going this way. But why are we left with this mess?
I don't know.
We are left with this mess because electrons had yet to be discovered on a microscopic level. It was not known that electrons were negative. They just knew that there was this negative terminal. So by convention, the current always comes out of the plus and goes to the minus, even though we know that electrons are negative and therefore they must come out of the negative and go all the way back to the plus. So that's one of those things to just know and then say, okay, I know it, but I don't care. We're not going to use it like that because it's all screwed up. And it is. It's all screwed up. But there's nothing we can do about it because it's been like that for about 170 years.
But you understand it in vacuum tube theory.
Yes, you do, because you have electron flow.
Yeah.
Yes. Okay. Is everybody ready for a 5-minute break?
Yeah.
Yep.
Okay, I'll be back in a few minutes.
Done deal.
Five-minute break, so be. Hey, Papa.
All right. Well, we're not starting up yet, but does anybody have any questions yet?
How did you get 60 for the 120 volt battery, 170 actual wavelength?
Oh, no, it's 170
Question?
volts. Yeah, okay. Well,
Whatever.
that's okay. Well, here we go with that. All right.
We just shouted out 60 and moved on.
Yep,
And
yep.
how did we get that?
Okay. See, I love it when people ask questions like that because that is really actually very important. So, okay, what I'm going to do is I'm going to do the next form of Ohm's law because we know that E is equal to I times R, correct? We said that. This is the second half of Ohm's law. We can do the same circle, PIE. Right? So there's EIR and PIE. This is the power version of Ohm's law. This is measured in watts. And you have to know what power means in order to understand the other part. So this is what we're going to cover right now because you asked.
Awesome, because I thought I asked a question that we covered previously.
Nope.
So.
Nope.
Wait,
Awesome.
P is power?
P is power. And that's measured in watts, big letter W. Okay, so let's actually start because that's been about 5 minutes. Okay, so here we go. What is a watt? A watt is a unit of energy production or use. A watt is a joule per second. A joule is a unit of energy. What is cool is that joules, which are a unit of energy, we know that energy can neither be what, everybody? Let's see if anyone knows this.
Still.
Nope.
Can neither be destroyed nor created.
Energy can neither be created nor destroyed. It only changes form. Okay, so we can have energy that is stored in a battery. We can have, that's chemical energy. We can have thermal energy. We can have potential, which is stored, so basically waiting to turn into something. We can have kinetic energy, which is energy of movement. But basically all of those are forms of energy, and they're all measured in joules, independent of how they're made or how they're stored. They just change form. So a watt is a production or consumption of 1 joule of energy per second. What's really cool about this is that the next form of Ohm's law, which is P equals I times E, gives us our electrical connection to it. So if I have a circuit which has a battery, we're going to draw that right now, and let's say this is a 10 volt battery, and here's my resistor, and that's a 10 ohm resistor. By Ohm's law, can we figure out the current? I think we can. So we don't know, we use the first circle, we don't know the current. So I is equal to E divided by R, which is equal to E, which is 10 volts, over R, which is 10 ohms, which is 1 amp. Okay, now that we know what the current is, and we know what the voltage is, can we figure out the power? I think so. P is equal to I times E. Well, we know our voltage, we know our current. Our current is 1 amp, and we know our voltage, which is 10 volts, which is 10 volt amps, and by definition, a volt amp, if they are in phase with each other, because they actually are sine waves, if it turns out that the phase, they're out of phase with each other, then you actually have to multiply it by the cosine between the two angles. But since we're not messing with that right now, a volt amp, for all intents and purposes, is also known as a watt. So we have 10 watts. So we now have the fact that how much power is our battery in this case supplying? How many watts?
10.
Okay, so the battery is supplying 10 watts. Where is the power going?
Stored.
No, where's it going? It's got to go somewhere. It's got to go somewhere.
Heat?
Comes out as heat. Comes out in the resistor. The resistor makes heat. So we are now converting power in electrical form to heat. And how much heat? 10 watts.
10 watts.
And a watt is a joule per second. So if we are using that to heat something, we can figure out how many joules per second it is. Let's say we're using it to heat water. We know what the heat capacity of water is. We can figure out how many joules per second it takes to heat water at a certain rate. This has a name. What's this called? I'll give you a hint. It looks like this. And there's a pot on top of it.
Boiling.
Yeah, that's a stovetop, right? That's a DC powered stove. So now, one question I would have for you is, why would we want to use higher voltages to deliver the same amount of power?
Speed.
No, power is power. A watt is a watt. Let's say we wanted to deliver 10 watts.
Less energy.
No, same energy.
Over to cook your dinner.
Lower
right?
current.
Lower current, that's right, because power is equal to I times E. So let's say that we have two different voltage sources. We have 10 volts and we have 100 volts. And then also let's give us 1,000 volts. Let's say we really went overboard. and we want our power to be 10 watts. Okay, so we have 10 is equal to I times 10. In this case, our I would be 1 amp. We could also do 10 for the next case, I times 100, which is 0.1 amps. And another one, 10 is equal to I times 1,000. Oops, one too many zeros. Equals 0.01 amps. So why would we pick one over the other? Remember that other thing that we have? Remember that other thing that we have? E is equal to I times R. Remember that one?
We need smaller wires to transfer.
That's right. You need smaller wires because the bigger for resistance is a function of the wire itself. The bigger the wire, the more expensive it is. The bigger the wire, the lower the resistance. So if we can get away with if we can get away with a bigger resistance, we can get away with smaller wire to carry the same current, which also means that because wire is not perfect, E is equal to I times R, we have something called voltage drop. So let's say we're going to pick this, we're going to erase these, and we're going to go to the next logical argument here. So let's say that the selection that we picked for our little heater circuit was such that we went with our 10-volt solution. P is equal to I times E. We're going to draw our circuit. Here's our battery, like this. Like this. We went with our 10-volt solution, our 10-ohm solution. We have 1 amp of current. Okay? So this assumes that our wire is perfect. So let us pick a wire that's less than perfect. E equals I times R. And we're going to say that this wire has essentially an equivalent resistance of 3 ohms. That's a lumped thing for the whole wire. We already said we know our current. E equals I times R. But now we're calculating the amount of voltage that gets lost right there. So now we have 1 amp times 3 ohms. 3 volts. Well, what was our whole power supply to begin with? How many volts?
10.
How much voltage do we have left to heat the thing?
7.
7 volts. What if this is a piece of electronics that requires 8 volts to work in the first place? What's going to happen to it? Your voltage drop is now too significant for it to even work in the first place. This is actually a real thing. This is voltage drop that's caused by high resistance wires. So one thing we can do to fix that is we can buy really expensive big wires, or we can just raise our voltage, in which case it doesn't really make as big of a difference. Now the other thing that's important here is that if we have 2 resistors in series like this, essentially these are now in series. You have to go through them in order to get back to the end. These actually add together. So what would the total resistance now be?
13 ohms.
13 ohms, that's right. Now, if I were to have a really high voltage, I wouldn't really necessarily care so much. But if I had a really low voltage, this 3 ohms could actually be a really significant factor in here. Again, the other thing I could do is, because they're in series, if I went with a really, really big wire, I might have 0.01 ohms. If that were the case, would it make much of a difference? Yeah, not really. But now let's go back to our 3 ohm solution here. And let's say that in our wire, because we have 1 amp flowing, does that 1 amp have to go through the 3 ohm resistor?
Yes.
Yes, and the 10 ohm resistor. So inside that 3 ohm resistor, we can do our power calculation again. Well, we know that there were 3 volts that disappeared across that resistor. P is equal to I times E is equal to 1 amp, because the current goes through it, times 3 volts is equal to 3 watts. Well, so what's going to happen to that wire if it has to somehow dissipate 3 watts of energy? What does it's going to warm up? It has to come out somewhere. So what happens if that's the case? If your wire is really thin and it has to dissipate 3 watts?
You're going to fry your wires.
Or you could, let's say it's run underneath a rug.
You're going to set the rug on fire.
You set the rug on fire. That's right. That's exactly right. So there's another thing that we do to keep this kind of thing from happening. So let's say we have our battery again. And we have a resistor, which is, let's say this is a 120 volt battery, and this is a 10 ohm resistor. Okay, so we're going to do our formulas again. You know, it's funny. Everything comes back to Ohm's law. I mean, I've been working as an engineer for a long time now. 90% of the problems that I try to debug come back to Ohm's law. Even now, they're nothing more complicated than Ohm's law. If you know Ohm's law, you can solve almost any problem, at least get an understanding of it. So here's our voltage. Here's our resistance. We have our unknown current. Okay, so let's figure out the current. From here, I is equal to E divided by R is equal to 120 divided by 10 is 12 amps. Now we can do our power. P is equal to I times E is equal to 120 or 12 amps times 120 volts is equal to 1,440 watts. So this power supply, this battery, is making 1,440 watts. Where's it coming out? If it goes in, it has to come out. In the resistor. This has another name also.
Heating element.
That's a heating element in a space heater. Or a heating element in a hot water heater, whatever, you know, take your pick. So now, let us say that this heating element is rated for 1,500 watts. That is a power dissipation rating. Are we good or are we not good?
We're good.
We're good, yeah. Okay, let's say that some anomaly happens and instead somehow this heating element comes out and it's only 5 ohms. Now we're going to do our formula again. What's 120 divided by 5? That is 24 amps. So now we redo our formula here. This is 24 amps times 120 is suddenly 2,880 watts. Okay, what is the heating element rated for?
1,500.
1,500 watts. What's going to happen to the heating element?
You're going to burn it out.
It's going to burn out, yeah. Well, what if you are unlucky and this wire was built because the nominal wire current that was ever going to be handled was only 12 amps in normal operating conditions. So what happens if suddenly you're pulling a current of 24 amps through this wire?
The wire catches fire before your heating element.
Yeah, the wire might catch fire before the heating element does. If it's a hot water heater, maybe the wire catches fire. Well, what happens if this is a wire in the middle of the wall in your house? You burn your house down, right? So what we do in this case is we install something else, which looks like this.
Fuse.
Which is a fuse, which is an overcurrent protective device that is picked for a certain current. Above a certain current, because it gets hot also, it melts on purpose. So if this is a 15 amp fuse, if more current than that is experienced, what will happen is that this wire inside the fuse will melt, creating an open circuit, which basically breaks the circuit because it's no longer closed. And this goes away, and now you have an open circuit, and you've, instead of burning your house down, you just have to go figure out what went wrong. And that's why we use fuses. Okay, so Now what we're going to do is we're going to answer the age-old question of AC, alternating current. So if I were to draw this is alternating current. Here's my resistor. This is AC. What happens with AC? What does that picture inside there look like?
Sine wave.
A sine wave. Okay, so if this is my current, what happens during this time? Is it positive or negative? What do you think? Inside
Positive.
those two bars. That's my positive side, which means that my current goes this way. How about in the other half, on the right-hand side?
Negative.
This is negative. That means my current goes which way? That way.
Right.
So basically, the electrons change direction. Does the resistor care which way
No.
the electrons are flowing? The answer is no. All it knows is that when it's at its high point, you have the most electrons flowing down because E is equal to I times R. During that same time, P is equal to I times E. Does everyone agree with that?
Yep.
Okay. So then I could also say that I could substitute something in right here between these two and rewrite these and say that P is equal to E squared divided by R. I can go through it if you really want me to. But basically, as the voltage and the current go up and down, is the power constant? Yes or no? Considering that the voltage is continually changing.
The power is the same.
The power goes up and down too. Because what is my voltage right here?
0.
That's 0. How much power am I delivering when my voltage is nothing?
Nothing.
Nothing. How about when it's all the way at this end again?
Nothing.
Nothing.
0.
And how about right there at the left end?
0.
0. Where am I delivering my maximum power? Right there at the top. How about at the bottom?
Maximum power.
Maximum power, because E squared. What's a big negative number squared?
Big positive number.
That's a big positive number. So it doesn't matter to the resistor which direction it's flowing. So this device actually experiences power that looks something like this. It goes through these big peaks, but then it goes down to 0. Peak, 0, peak, 0. So it's not constant. Well, if it's not constant, how are you going to figure out what it is? Well, I mean, one way to do it would be, okay, I can take a resistor and I can stick it inside a box and I can heat up some water and run it for 10 minutes and see how much it heated up and figure out what the power that went into it must have been on average, right? Because I know that there's all these zeros and I know that there's all these peaks and there's all this stuff in between. So I could look at it and see how much power actually went in. Or what I could do is I could use mathematics and figure out what it was going to be. So if I want to figure out what my average is, how much average power went in, I can take a look at, because this is a squared term, I know what the power is at any given time. Does everyone agree with that? I know what the power is at any given time. Because I know what the voltage is at any given time if my voltage is going up and down. Right? If it's going to plus and it's going to minus, I know what it is. This is a sine wave. All I have to do is look at the angle and I know what that value is. So if I were to do that and I want to take an average, I would take an average over a period of time, which means I need to figure out what the total is over a period of time and divide it by the time. Like if I know that I go from here to here and this is 300 miles and it took 6 hours, how fast was I going on average? 50 miles an hour. Could I have been doing 200 miles an hour for a while and then taking a long lunch break?
Yep.
Yep. You can't tell. It doesn't really matter. Unless, of course, you got a ticket. Right? Or you probably end up in jail if you were doing that. But, you don't know how it got there. And to a certain, if you're looking from the outside, you really don't care. So all you want to do is find the average. And the way to find the average is you take something called an integral of the power, e squared divided by r, over 1 complete time, and e squared of t dt, and divide it by 1 time period. Now, this actually, because this is in a lot of cases a sinusoidal term, it actually is solvable. We're not going to do calculus today. This is the only calculus you're going to see, and I'm actually not going to solve it. What it really turns out is that for a sine wave, and we're going to draw a sine wave again. Okay, this is going to be, we're going to call this 120 volts. And this is called RMS, sine wave. This sine wave, when it's coming out of your wall, delivers, and this is why we do this, the same amount of power as a DC equivalent 120 volts would make. Somebody was asking about why you would see peaks of 170 and negative 170. Who was that? Come on, don't be shy. Somebody asked me that. I don't remember who that was. Okay. Well, it doesn't really matter. But so basically what you have is this 120 volt, as we call 120 volt power. And what you really have is a sine wave that peaks at, it's actually 120 times the square root of 2, and goes down to minus 120 times the square root of 2. Square root of 2 is 1.414, so it turns into plus or minus 170 volts. So where this comes into play is if you are building something that has a capacitor in it or something that is rated at 150 volts DC, and it goes across here, across the circuit, what will happen is, since it's rated at 150 volts DC, even though you really only are hooking it up to a 120 volt circuit, it's important to know what the peaks are. And what are the peaks? Plus or minus 170. And what will happen to your capacitor?
It'll blow up.
You'll blow it up. That's right. Because there's actually a higher voltage in it. And again, the reason that we do this is because we are figuring out what sine wave creates an equivalent amount of power as a DC current source. And again, this is called RMS, which stands for root mean square. And so the reason we do that again is because we're trying to figure out just how much power is being made on average.
What? I'm busy. I'm on the internet.
All right. Do we have any questions on that?
Nope, I got a headache now, though.
Okay. Well, we're almost done. There's only 20 more minutes today. So, but now you understand what is inside your wall circuit. It's 120 volts, but if you go to measure it, you'll actually see it going up and down and up and down.
I don't care if it's 30 volts. I'm not touching it.
Well, right. Well, 30 volts. Yeah, you can still get a zap from that. You still get a zap from 30 volts. Okay.
With no current, you won't.
Well, yeah, you might still feel, well, then you'll pull it down, but you might still feel a little something. Okay, so let's make sure that we got everything and everybody's good with that. Here's electrical principles. This is a circuit. We can all apply Ohm's law. Voltage is the push. It's called an electromotive force. The name of the flow of current. The flow of electrons in an electric circuit is known as current, and it's measured in amperes. Here's an alternating current. There's a cycle. I think we've all pretty much beat that dead horse. Um, alternating current alternates between positive and negative directions. The number of times in a second that an alternating current makes a complete cycle is frequency. The unit is hertz. Units of electrical resistance. Oh, one thing we didn't cover. Let's name some good conductors. A conductor is something that allows current to flow nicely. Let's name what?
Water.
What kind of water?
Salty water.
Salt water. How about deionized water?
That one too.
Actually, deionized water is a terrible conductor.
Has no minerals.
Yeah. Well, deionized, demineralized. Yeah, it's a terrible conductor. Other things that are good conductors? Copper. Yep.
Glass.
Glass is terrible. Glass is an insulator.
Yeah, glass is an insulator, right?
Yep.
Gold.
Gold.
Titanium.
Silver. Copper. The nice thing about actually copper's better than gold, but gold doesn't tarnish. So that's why people use gold conductors. Whereas
these things,
let's see, aluminum.
what is it that makes all these materials?
What?
The density?
Wait, what was the question?
What is it that makes something a good conductor versus a not good?
It's
the
density
of the
No, it's the degree. It's the degree to which the outermost electrons are held in place. So typically a good conductor, a good conductor will have a lot of extra electrons that are kind of like far away from the nucleus, so that if one drifts away, the nucleus really doesn't care a whole lot. So basically, if it's a big atom and it's got a couple of electrons that are sort of flying toward the outside, if there are a few electrons flying loosely around the outside, another one can pop in, and the other one disappears pretty easily. That makes a good conductor. Aluminum is a really, really good conductor, but why don't we use aluminum wire very much?
It's too
Higher
soft.
resistance.
Actually, it's not.
It heats up.
Yeah, actually, it doesn't. It does a little, but aluminum wire is really lightweight. It's pretty cheap. Why don't we use it more?
It corrodes.
It corrodes. That's right. And the thing is that aluminum oxide is a terrible conductor. So what happens is you get this conductive material, and its surface gets covered with a non-conductive oxide. And then you end up generating, because it's a high resistance, you end up generating heat. And what does that do?
Burns your house down.
Burns your house down. That's right. And in fact, there was a string of house fires that were caused by improperly installed aluminum wire back in the 70s, before they figured out you could use aluminum wire, but you had to treat it properly. It had to be in an airtight, watertight jacket when you made the connections. Otherwise, it would corrode, and then it would oxidize, and you'd burn your house down. So,
well, that's why they had the tubes and knobs.
Yeah. Let's see. What is a good insulator?
Glass.
Glass. What else?
Rubber.
Rubber. What else?
Wood.
Wood is pretty good unless it gets wet, unless it's been sitting in salt water. What else?
Oil.
Depends on the oil, but yeah. Other things?
Teflon.
Teflon, yeah. Polyethylene, a lot of plastics, a lot of ceramics. How about some other ones?
Fiberglass.
Fiberglass. How about mica?
Mica's one of the best.
Mica's a really good one. Mica is a natural mineral used for insulation.
Used for capacitors.
Yep. Actually used for used as washers for high voltage connections.
Silicon.
Silicon, yeah. Again, actually, silicon is a tricky one because it is, but it's also thermally conductive in a lot of cases. So it has to be like silicon grease. It's tricky.
Yeah, some of them they're conductive, some of them are not. If you use your own meter, you can tell which one it is.
Yeah. Okay, Ohm's law. I think we beat Ohm's law to death. If anyone has any practice, you can go through all these practice questions and not just memorize why it is, but what it is and how you get it. We should all be able to do that at this point. Series and parallel circuits. Two resistors that are in a row are in series because every electron to get from the battery back to the battery has to go through both of them in series. If there are two resistors that are parallel, like they're parallel lines, that means that any electron has a choice to make. It can either go through one or the other, and it divides the current. It splits it. So if your, for instance, your battery goes like this, your crudely drawn battery, and it goes like this, and you have R1 and R2, your resistances add together because every electron is tasked with going through both of them. That is known as a series connection. Resistances add. If you instead have a circuit that looks like this, where you have the choice to make of going one way or the other, then you have R1 and R2, then the current will be whole here, and some of it goes this way and some of it goes this way. When they rejoin, you'll have the same current I flowing through here, but you'll be I1 over here and I2 over here. It will split. So which way do electrons want to travel?
The easiest way.
Yep, path of least resistance. So if this is a very low resistance and this is a very high resistance, which way will most of the electrons go?
Low.
The low resistance path. That's right. Now, if these are equal resistance, what are you going to do?
Divide the current.
Yep, you're going to split it in. You're actually going to split it directly in half. So as it turns out, if each of these is a 10 ohm resistor and they're equal, you're going to have a combination resistance as viewed from the outside as R1 R2 over R1 plus R2, which is 10 times 10 divided by 10 plus 10 is equal to 100 divided by 20, which is 5. So if you have two resistors of equal value in parallel, you're going to get half the resistance. If I have a combination of 10 and 10 and 10, what do you think you're going to get?
3/3.
33.
Yep, 3.3. They're going to divide by the factor of 3. And you can go through the math if you want to do this. But now, one thing that's important to note is that, again, if these resistors are different values, what's going to happen to your currents? Are they going to be the same or different from each other?
It's going to be proportional.
They're going to be they're going to be proportional to the resistances. So you're going to have that's known as a current divider, and it's going to be proportional to the resistances. Similarly, I could draw this, like I could do this. I could have this being a 10 volt resistor, and this being 7 ohms, and this being 3 ohms. And what is my total resistance of that?
1.
10
ohms. Okay. Now, how much voltage of those 10 ohms, if I were to measure across this first resistor, the 7 ohm resistor, what would my voltage measurement be right here?
7.
That'd be 7 ohms. How about right here? How much?
3. 3.
It would be the other 3. And if
No.
the other thing was called a current divider, this is known as a
Voltage divider.
voltage divider. That's right. This functions as a voltage divider. So this allows you to, let's say you have a 10 volt circuit and you need a separate circuit that runs off of this circuit to power some little piece of electronics that uses 3 volts. You could actually do this to generate a 3 volt circuit. Oops. There, 7 volts, 3 volts. And that's known as a voltage divider. Now, if these resistors are exactly the same, what's going to happen to your voltage division?
The half.
It'd be exactly half.
50%.
That's right. So if they're not equal, then they're going to be proportional to the resistors. Okay, so now one more thing also is, let's say that this is we're going to replace the battery with a battery that looks like this. And what does that indicate, everyone?
AC.
AC, okay. So let's say this is 120 volts AC. And you have a resistor and a resistor. And actually, inside each of these resistors actually looks like this. What does that look like?
Heating element.
Light bulb.
Oh, light bulb. Yeah, okay. So let's say that each of those is actually a light bulb. And you blow out the first element of the light bulb, the first one. What will happen to the second light bulb?
You want light.
It won't light. Yeah, you'll have power out. So this one will actually go dark. What happens if you replace it and you have a very low resistance, like a short circuit right here? What will happen to the second light bulb?
You'll burn it out.
You'll burn it out because you'll get the full voltage across it. So what is this an example of? Where do you find something like this?
Christmas tree lights.
Those are Christmas tree lights. That's right. And that's why Christmas tree lights that are all in series tend to have problems, because if one burns out, they all go out. So why don't we wire our houses this way?
You never find your burned out light.
That's right. So instead, in our houses, we wire a voltage bus. Like if this is 120 volts AC, what voltage is over here?
120.
120 volts AC. How about way over here at the other end of the house?
120.
120 volts AC.
Minus
it's a little voltage
loss.
drop because of the wire, right? But by and large, you basically have the same voltage everywhere. The more things you add, though, what happens to the current that has to go through this wire right here on the left? The more things you're powering,
the current goes up.
The current goes up. So let's say you have put a fuse on your main panel that's a 20 amp fuse, and you have this thing that that pulls 3 amps, this one that pulls 6 amps, this one that pulls 8 amps, and this one somebody plugs in a microwave oven that pulls 12 amps.
And poof, you gotta go to the board.
You got to blow your you'll blow your breaker or blow your fuse, depending on how it's wired. But that's why we wire our houses in parallel. That's exactly why. So we don't have lights that dim unexpectedly and things like that. Okay, so here's power. We're on DC power. We can calculate all those. You can practice those all you want. All right, the last thing we're going to do today is math for electronics and units, and we might get to do decibels. So this is a pretty quick thing. I'm not going to get too deep into decibels, but units. So a unit is a thing. So let's say a volt, right? And we're going to add something in front of it called a millivolt. Milli is a little letter M, and it's shorthand for 0.001 times it. We could add a micro, which is 0.000001. Why would we do this kind of thing? Because let's say if we had 0.000006 volts, do those zeros really mean anything to us? Not really. The only thing that's important is that number 6, right? So we have 6 times 0.000001 volts, that's micro, so we have 6 microvolts. If we had 6.3, we'd have 6.3 microvolts. So what's important is whether or not we actually have any precision in our number. The micro or the milliwatts or the picowatts or the kilowatts, those are just placeholders for a bunch of zeros. If you think of it like that, you just have to memorize them, but they're all very standard. You just have to memorize them. And you can convert them. For instance, milli, if you know that milli means 10 to the minus 3, which is the same as 0.001, 10 to the minus 3 means you start with 1 and you go 1, 2, 3, and then put in zeros. 10 to the minus 6 means you start with a 1, go 1, 2, 3, 4, 5, 6, 0, 0, 0, 0, 0, 1. You go the other way, 10 to the 3 is a kilowatt, 1, and you go 0, 0, 0, and you're at 1,000. Similarly, we can do this, we can convert back and forth. If you know that you want a certain number of zeros, you can convert milli to micro or kilo to mega, for instance. So big M is mega is 10 to the 6th, 1, 0, 0, 0, 0, 0, 0, which is a million. So you can convert a kilo to a mega by moving zeros around. So that's units. And they make a big deal of units, but to be honest, units are just a way of moving zeros. So can everybody see that table right there?
Yep.
Okay. That table, it's good to go through that table. It's good to go through that table and do some conversion things. And it's all just, if you just think, okay, 1.5 amps, we want how many milliamperes? So in other words, if you look at a 1, how many 1,000ths are in a 1? There are 1,000 of them. So it's really just moving zeros around. Like 1,500,000 hertz. Well, you can convert it. You can say that's 1.5 million hertz, which is 1.5 megahertz. Or if you move them around, you only take 3 zeros out. That's 1,500. But then you have to take the 3 zeros that you took out and replace it with kilo. So that's something that, we just go through and do the math on and move zeros. Okay, decibels are a little more complex, but at the same time, not really. And this is going to be the last thing we cover today. So a decibel came from Alexander Graham Bell. That was a unit of comparing one thing to another. So there's something called a logarithm, which is an inverse to this thing called an exponent. This all comes back to that same zeros thing. So we know that 10 to the third is 10 times 10 times 10, which is 1,000. Notice we start at 1 and we go 1, 2, 3 places, and we have 1,000. Well, okay, so the log, which is kind of like the inverse function of doing 10 to the something, is the log base 10 of something is the power to which 10 has to be raised to get to a certain number. So if I look at log base 10 of 1,000, the way to get there is I would say, well, 10 has to be raised to what power to make 1,000? That's 10 to the third power. Well, the log is that number. So it's kind of the inverse of doing an exponent. Similarly, if I were to do like log base 10 of 10 to the 3, very simply, 10 to the 3, this inverts it, and it's just 3. So this is actually known as the formula for a bell, and it's a way of comparing two things with each other. So if I were to do the log base 10 of P2 divided by P1, that is known as the number of bells. So if something is 10 times the ratio of P2 over P1, log base 10 of 10 is the log base 10 of 10 to the 1, because 10 is equal to 10 to the 1 power, is just 1. That would be 1 bell. But then somebody figured out that the bell was too small of a unit, So they created something called a decibel, which means tenths. So it's 10 log base 10 of 10 to the 1 is 10 times 1, because this is still 1, just like it was, is equal to 10. And the unit is dB, or decibels. So where this comes into play is when we are comparing two things together. We are comparing a starting point with an ending point. And we want to know how many, or what order of magnitude bigger the ending thing is than the starting thing. So if we started at 1 watt and we went to 10 watts, that would be a ratio of 10. And then we can figure out, okay, we went up by a factor of 10, that's 10 decibels. Let's say we started at 2 watts and we went up to 4 watts. Well, that would be a ratio of 2, in which case it turns out if you go through the math, this is not something you have to calculate, but you do have to memorize it. That's 3 decibels. So this is 2 times, and this is 10 times. These are the things that are critical just to commit to memory.
What's 6 dB?
6 dB? Well, okay. Decibels add together. So 6 dB is equal to 3 plus 3. Well, we know that 3 decibels is how many times?
2.
2 times. And 3 decibels again is?
2. That's 4.
Yep. 4 times. So 6 decibels is the equivalent of, let's say, going from 3 watts up to 12 watts. That would be 4 decibels, or sorry, 4 times, or 6 decibels. And the reason that we do this is because decibels are a really convenient way of taking really big numbers and making them easy to work with. For instance, if we go a starting point of 10 to the minus 12 watts, and we end up at 1 watt. So we have 1 divided by 10 to the minus 12. Right? Does anybody raise your hand if you want to deal with all those zeros?
No.
No. So by definition, this right here is 10 to the 12th power. If I take going through my decibel formula, decibels is equal to 10 log base 10 of that. Well, this right there is 12, is equal to 10 times 12, is equal to 120 dB. So that's a gain of 120 dB. It's 10 to the 12th larger. So it's a trillion times bigger, but we can just represent it as 120 dB. Where this becomes very convenient, we can do losses also. If a gain is positive, a loss is negative. So a doubling would be 3 dB. A loss of doubling of a half would be negative 3 dB. Without having to go through too much effort, you could say that if I go through a block that has a 3 dB gain and the next one has a negative 3 dB gain, which is a 3 dB loss, here's my input and here's my output, what would the end result be?
2.
Equal?
Well, let's say whatever the in is, plus 3 minus 3, what would the output be? In plus 3 minus 3 is equal to what?
In.
It's the same as the input. That's right. It didn't change. No change. That would be a gain of 0 decibels. So very, very convenient way of doing things. So really, the only things that I ever think about when I'm dealing with decibels is that 3 dB is 2 times. 10 dB is 10 times. And you can basically, you can get an approximation from these for virtually any number. Let's say I had 117 dB. All right, let's add them together. Okay, Using 3s and 10s, how do we get to 117? Good question. Well, we could go 10 and 10. We could do 12 of those. That would get us to 120. Right? And then how do you get from 120 to 117?
Minus 3.
You could subtract 3. Yeah. Okay. So that would be 120 dB, which would be 10 times 10, 12 times. And then what does the minus 3 decibels mean? That means a half.
Half.
That's right. So it's 10 to the 12th power times a half, or 5 times 10 to the 11th, if you really wanted to know. And what's nice about that is that this is still way cleaner, isn't it? But if you wanted to actually know, let's say that I put in a certain amount of power, how much I was going to get out, you would actually have to do this. But you can do most of this stuff just by scribbling it down on a piece of paper. So nice, easy shortcuts.
Okay.
Everybody good with that so far? There's a lot of stuff to
Yes.
know, right? But what I hope is that the stuff that we are doing here, the stuff that we are covering, some of the theory behind it makes those memorization things make some sense. Why is it this way? This is why it's that way. And you can always go back to, I remember that 3 decibels is 2 times. Well, if you're there and you have an antenna that has a gain of 9 decibels, okay, well, 3 times 3 times 3 and 3 and 3, that's 2 times 2 times 2, which is 8 times. Okay, so if I put in 1 watt, it will be like I'm getting 8 watts going that way. That can help you make some decisions.
Well, Scott, I want to say I appreciate your time. I really appreciate this.
I appreciate everybody being here, and thank you.
Thanks.
I'll stick around if you have any questions. Anybody who has any enrichment questions, or there's just something that they don't understand yet.
Thank you, Scott.
Thank you.
Thank you.
Posting this online, right?
Thank you.
Thank you, Scott.
All right, we'll see you guys tomorrow morning.
Never heard.
Appreciate
I'm gonna
you.
post the class online, right?
Yep, I'm going to hit stop.